அட்மிஷன்ஸ் எல்லாம் வந்தீங்களா? முடிச்சிருந்தவா?
Hello, ma'am. Can I start the welcome address?
Yes, yes.
Hello, everyone. It's my great pleasure to welcome you all to the Atal Faculty Development Program organized by Marthanam College of Engineering and Technology. We are honored to have such a distinguished gathering of faculty members and researchers who are eager to enhance the knowledge and skills in the field of MRI physics for image acquisition. Today, we are privileged to have with us an exceptional resource person, Dr. Sydney Williams, whose expertise and accomplishments are truly inspiring. Dr. Williams is currently a lecturer at the Imaging Center of Excellence at the University of Glasgow, UK, where she is specialized in biomedical engineering and magnetic resonance imaging. She holds a PhD in biomedical engineering from the University of Michigan and has an impressive academic background, including multiple master degrees in electrical and computer engineering and also biomedical engineering. Dr. Williams had made significant contributions to the field of MRI, particularly in the design of radiofrequency pulses and parallel transmit arrays for ultra-high field MRI. Her research has been published in the top-tier journals such as Magnetic Resonance in Medicine and Physics in Medicine and Biology. She has been invited to speak at numerous international conferences, including the International Society for Magnetic Resonance in Medicine. Her work has not only advanced the technical aspect of MRI, but also have paved the way for improved clinical applications. In addition to her research, Dr. Williams is deeply committed to teaching and mentoring. She has developed and delivered courses of MRI physics, cognitive brain imaging, and medical imaging, and has supervised several postgraduate students in their research endeavors. Her dedication to education and innovation is evident in her leadership roles, including organizing international workshops and serving as a deputy for innovation and engagement at the University of Glasgow. We are truly fortunate to have Dr. Williams share her knowledge and insight with us over the course of this FTD. Her expertise will undoubtedly enrich our understanding of MRI physics for image acquisition and inspire us to push the boundaries of our own research and teaching. Once again, I extend a warm welcome to all participants and express my gratitude to Dr. Williams for joining us. Thank you.
Thank you very much for that warm introduction. I hope that everybody can see my slides okay. I think so. If not, please feel free to interrupt and let me know. So yes, today I will talk to you mainly about MRI, magnetic resonance imaging physics and acquisition, some of the general principles for how MRI works. I will also talk a little bit about a special type of MRI called ultra high field, and this will be a nice transition for the speaker that follows me, Dr. Shajan Gunamani. If anyone has any questions, I welcome you to interrupt and to ask or to write them in the chat. I'm happy either way. Thank you. So I just wanted to put together a quick little bit of an index of what we are going to talk about today. First and foremost, I want to motivate you to appreciate MRI, why you might want to learn about the technical aspects of it. And I'll do that for showing just general applications of MRI and medical imaging in general. Then I'll go into the physics of how MRI works through the process of nuclear magnetic resonance. I'll talk about the hardware that you use to build an MRI scanner. And then I'll talk about MRI imaging in general based on parameters and the tissue contrast that you might get from these parameters. Then talk about how you actually collect an MRI image using all of these concepts. An important aspect that I would like to touch upon today too is safety with relation to MRI. And then in the latter half of the presentation, I'll turn to the special area of MRI called ultra high field and why we might want to do it, what are some of the challenges associated with it, and where are the key applications in it. And it's primarily in neuroimaging at the moment. Okay, so let's go into MRI. So MRI is a relatively recent imaging modality. First started to be developed during the 1970s, both in the United Kingdom and the US. And it's pretty much taken off nearly exponentially since then. And right now there's, as said here, around 50,000 scanners worldwide. But unfortunately, one of the challenges with MRI is that distribution of scanners is not very equitable in relation to populations. It's definitely true that because it's a very costly modality, it seems to be more prevalent in richer countries. But on this little Venn diagram I've borrowed over here on the right, you can see some of the various advantages and disadvantages of MRI compared to other modalities that you might have heard about for medical imaging, like CT or X-ray, or something called positron emission tomography, PET, or ultrasound. They all have their advantages and disadvantages for you might want to use them. But the primary reason why you would use MRI is because of the excellent resolution that you can get, very high resolution, and really, really nice contrast between different types of soft tissues in the body. So this is something that you won't see with ultrasound, you won't see with CT, but when you look at the image of an MRI of the brain, you really can see the different constitution, like the different ways that the brain is constituted between gray matter and white matter and CSF or cerebral spinal fluid. And this type of thing makes it a really powerful modality, especially for neuroimaging, like I mentioned. So here's just another way that you could compare MRI. Not only do you get that really great contrast and high resolution, you also get full body penetration. You can also see a 3D view of the body with something like computed tomography, CT, but other modalities are more superficial. Even ultrasound can't penetrate fully. There's, an amount that the ultrasound waves can transmit through, not very much in the brain because of the skull, and so therefore you have limited depth penetration in other types of modalities. So that's why we'll talk about MRI. Why I'm passionate about it is because I think that it offers a lot for a lot of clinical applications. So this is something that's just general to all medical imaging. It's the trade-offs that you need to consider, though, to get a really good MRI image or a CT image or an ultrasound image. There's always a trade-off between spatial resolution and temporal resolution. So this means that if you want to acquire an image really fast, you probably have to compromise on the amount of data that you can collect, and that would be directly related to the resolution of your image. There's another concept, though, related to that, and that's called the signal to noise ratio. Because yes, maybe you could scan forever and get as much data as possible, but you'll only able to, the resolution you'll ultimately be able to have is limited by the amount of signal that's actually available to you initially. So you could kind of imagine this in this little pictorial diagram here, how if we have a certain amount of signal molecules available, let's say, um, if I make a really small pixel box around them, I'm going to be having more noise relative to the amount of signal. And therefore, even though I have high resolution, it will be noisier due to a lower signal to noise ratio. However, if I made the pixel itself quite large, I would capture more of those signal molecules and then have a higher ratio of signal to noise. So we have to also consider the amount of signal to noise that's relatively available. But we can't, we have to find a sweet spot between this resolution that we want, the time that we're allowed to scan for a comfort scan session, for a comfortable scan session, and then signal to noise. But if we don't scan with a high enough resolution, we have other problems as well. So this is demonstrated with something called the partial volume effect. So on the left, we can see an image of the brain, and you can see already it looks a little bit blurry, but that's not because of the signal to noise ratio. That's actually because of what we call partial volume effect. And essentially, we have different tissue types that are being captured within the same pixel, or in imaging, we call it a voxel, because it's a three-dimensional volume. And so in that case, where the red arrow is pointing, what we're seeing is part of the orbit of the eye is being captured in the same voxel as some of the space in between. And therefore, we get this kind of blurring of that line. And then when we go to the right-hand side, when we've actually used an appropriate image resolution, we've got rid of that blurring of the two tissue types and the partial volume effect. So this is what might happen is even if you have the signal available, if you try to cut down on scan time and acquire too low of resolution, we unfortunately have other problems like this partial volume effect. But relatedly, on the other side of things, if we scan too high of resolution, we take too long to scan, maybe the person inside the MRI scanner will start moving, and then we'll have what are called motion effects. So the longer you scan for, the higher resolution, the more susceptible you are to motion. So all of this is to say is MRI is a beautiful modality, but it's subject to some of the same considerations you'll have with every medical imaging modality. And that's kind of the part that I'm really passionate about in my research is how do we find solutions to these challenges that are kind of equal and opposite and related. So these are just a few, even though it looks like many, of the applications of MRI, and they're primarily based around neuroimaging because it is true that for imaging in the brain, MRI is the dominant modality and what I have the most expertise in. So as you can see, There's quite a lot of things that you can do, and all of these kind of come with different imaging styles and contrasts. But the ones in bold, I'm going to just walk you through right now so you can get a little bit of a flavor of what you could do with MRI. So, first, most common is anatomical imaging or imaging of the structures of the brain. These are actually images that we acquired at the University of Glasgow at the Imaging Center of Excellence, where we have a special type of MRI scanner I'll talk about in a little bit. So on the left, we have one type of the brain that's one orientation of the brain, kind of a cut through like this transversely, and then the other one's an opposite orientation going, through the center like this. Both of these images are in the same person, but you'll notice that have kind of opposite contrasts, and that's because they're acquired with two different types of MRI scans I'll talk about. We also have functional MRI, so it's kind of the analog to structural MRI. And here, what we're doing is we're actually seeing the functional activity of the brain. This is done by noticing differences in the blood oxygenation level of the brain that is in response to some sort of neuronal activity. So it's really useful for cognitive science because you can understand what parts of the brain are active with certain tasks. These are showing two different papers with this sort of example. The one on the left is really nice because you're actually seeing it layer specific. So along the cortical layers of the brain, you can see the different activity levels. Another type of thing that's tangential to imaging in MRI is MR spectroscopy, which is actually looking at the spectral profile of different metabolites in the brain. So rather than collecting the main signal that we use for MRI, which is proton or the water signal, we saturate that signal and we look at other types of macromolecules in the brain. And it's important for understanding of certain types of disease. So on this example on the right, we're looking at a map of different spectroscopic or spectra that are collected. And here we're seeing just different types of content for different metabolites like choline or different lipid signals, water, in relation to a brain tumor. So you can see that there's different metabolic activity in the tumor in the brain. This is another example. This is diffusion weighted imaging. This is a really important type of imaging, especially for stroke imaging. It's related to the diffusivity of axon fibers in the brain. So on the left is just an image that's weighted by the diffusion itself, and on the right, it's actually a tensor image that was created from coloring the dominant direction of diffusion in white matter tracts of the brain. Another really awesome type of imaging we can do with MRI is MR angiography. So this is actually showing the arterial system of the brain. And on the left side, you can see a map that was made showing where different feeding arteries flow to within the brain, within the arterial network there. And then on the right is actually an image, again, we collected in Glasgow, that is very, very high resolution, about 0.2 millimeter in plane. And you get some of the type of small arterial details that you wouldn't get in other types of scanners. So that's just some nice ways to motivate you about the nice types of images we can create with MRI. But how do we actually do that? We can start at the physics with a process called nuclear magnetic resonance. So this is the principle for which MRI can be performed. So essentially, if you have an atomic nuclei that has an odd number of protons or neutrons, it will possess what's called a magnetic moment. So say we have some water protons sitting here. We talk about water most of the time because that's the dominant proton that's existing in the body. And also it's very sensitive to nuclear magnetic resonance. It generates a large amount of signal. So it's a nice thing to use. And this is exactly what I've just said. So 2/3 of the body is water. So it's abundant and it's easiest for us to access in MRI. So when we place these atomic nuclei in a very, very strong external magnetic field, they do this thing where they become polarized and they align themselves parallel or sometimes anti-parallel to that magnetic field. So that's shown here. And actually the majority of which are going to be in the parallel direction. The number of spins that are parallel relative to anti-parallel is related to that strength of the main magnetic field. So they have this polarization, but then they also will exhibit this thing called precession along that main magnetic field at a very specific frequency called the Larmor frequency. So this precession is kind of often compared to when you spin a top, but in the reverse sense that rather than spinning and falling down, it's falling down and it spins to go back up to the direction of the main magnetic field. And this Larmor frequency actually increases with the strength of a magnetic field. So you've probably heard of a 3 Tesla MRI. And so that is associated with a Larmor frequency of 128 megahertz. And we'll also talk about 7 Tesla MRI today, which is then 300 megahertz, and et cetera. So basically, if we want to measure this precession of spins, we can't do it when they're aligned to the direction of the main magnetic field because that is going to dominate any signal that we could ever collect from these atomic nuclei. So what we do instead is we apply an external radio frequency field at the Larmor frequency that they're sensitive to, and that causes those protons to very quickly tip away from the direction of the main magnetic field into the transverse plane, so orthogonal to the main magnetic field. But because the main magnetic field is really strong, they're going to quickly precess in that top-like motion all the way back to the direction of the main magnetic field. When they start doing that precession, because it's now perpendicular to the main magnetic field, we can use a radio frequency coil to receive that precession. And that signal that we receive from it is the MRI signal that we use to make an image. So basically, when it's spinning, we're going to collect a signal that's oscillating, and the signal will become weaker and weaker with time. And that oscillating signal is called the FID, or free induction decay. As it recovers, we call it recovery when the spins go back to the direction of the main magnetic field. That process is known as relaxation. And we have two sort of constants that we characterize these atomic nuclei with in terms of relaxation. There's one that's called T1, and there's one that's called T2, or sometimes T2 star. So T1 is the easy one to understand. It's the longitudinal relaxation, and it's that process of those atomic nuclei after they've been excited with some radio frequency field. It's the process for which they want to return back up to the main magnetic field direction. And in general, we call this a relatively slow relaxation time because it might be on the order of seconds even. But what is nice to know about it is that different tissues kind of have slightly different water contents, and so they will produce different relaxation times. And that's exactly where we get the really beautiful tissue contrast in MRIs because of these differences in relaxation times. So this is a nice diagram on the right, and it's showing you between fat, liver, muscle, and cerebrospinal fluid, we have different rates of recovery for T1 relaxation. The other type of relaxation is transverse relaxation, or T2. And what this is when I was talking about this whole process of nuclear magnetic resonance, we were thinking about a single atomic nuclei being aligned to the main magnetic field, then being perturbed, and then precessing. And that's one way to think about it, but actually it's happening on the scale of many protons precessing. And as they precess, they might become out of phase within each other, and as they dephase amongst each other, then they're going to also cancel their signal out relatively quickly. And so that's where T2 relaxation comes from. And it's relatively fast, when this time it's on the order of milliseconds. And just like we had before, there will be different T2 times for different tissue types. So again, we can use that to our advantage and get some type of unique contrast between tissues with MRI. But then one additional thing about T2 is that it's not just susceptible to the different components of tissues of protons that will spin and become out of phase with each other. It also is sensitive to the main magnetic field itself being slightly non-uniform or inhomogeneous. And if there's inhomogeneities in that main magnetic field, that will also cause them to dephase even faster. And that process is called T2 star. Okay, so that's some of the MRI physics. We've kind of understood what's happening on the atomic level, but let's think about how we actually create the process, or how we build the equipment to be able to do these type of experiments and measure these signals. So we'll look at the MRI hardware. So this is a pretty old diagram, but it's still quite useful for showing all the different layers of kit that go into an MRI scanner. So you'll see that if you've seen an MRI scanner, and I had one on the first slide, it looks like a big donut. It can be a bit intimidating, and in fact, it can be claustrophobic for some patients when they go into the MRI scanner because you're within this big tube, and it's a tight fitting tube. So how like what is the use for all of that machinery and what are the different components within? Well, usually in most MRI scanners, not necessarily the 7 Tesla scanner that we'll talk about today, you need the radio frequency coil, the RF coil that's going to create the field that will both excite those atomic nuclei and also receive the signal from them. It needs to be as close to the person as possible because if you remember, the main magnetic field itself creates a very strong um, signal of the spins all within the longitudinal direction, and the precession of those spins when they're knocked off and perpendicularly is a lot weaker. So we got to get the radio frequency coil close to the subject in this case. So that's why it's on the inner layer. Then beyond that, we have something called gradient coils, which I'll talk about itself. And then of course, the main tube itself is actually the magnet that's creating this massive magnetic field that's having the ability to polarize all the atomic nuclei in the body. And then associated with those three sort of components in the MRI scanner, you have all of their electronics too, because you need to amplify things, you need to digitize signal. So that's what all the external electronics are about in this diagram. Here's another way to look at it, a little bit more realistic of a cutout in the modern scenario. So we'll first start with the really key part to an MRI scanner, which is the main magnetic field. How do we make the magnet? Magnets will have varying field strengths for how strong they are. And we'll talk about why we have different field strengths. Magnets also can be made from different types. Overwhelmingly, most MRI scanners use what are called superconducting magnets, but not always. So we'll talk about that. And then, when you see a typical MRI scanner, it's going to look exactly like this diagram where they're kind of oriented so that the main magnetic field points in the direction for which that person is lying in the scanner. But there are other configurations available. So if we go to how do we generate the main magnetic field? So this is just a brief reminder of electromagnetic physics. So if we wanted to produce a magnetic field in a straight wire, we would run current through it, and the magnetic field would be related indirectly proportional to the distance away from the wire. And then if you had a coil of wires, it would also be related to the permeability of free space and the number of turns of that wire. So this is kind of the classic example of a solenoid magnet in the right hand over here. So we can think about, okay, what if we just did a very, very, very tight, wounded coil and we could build this really massive magnetic field that we could use for imaging. I'm sure that would be something that would be a good idea, probably. But unfortunately, that won't quite get us to the type of magnetic field strengths that we need for MRI. So what we need for MRI is we need an extremely high magnetic field, and we need it to also be very homogeneous, which means that there should be very little deviation in the magnetic field. But you imagine if you look at the picture back here, when you have these very large magnetic fields, you also have fringe fields that come out directly in line with the direction of the magnetic field. And if we have a very strong one, maybe those fringe fields themselves are quite large, and that could be a bit dangerous. And that's shown here in this example where the red line is shown. These are the fringe fields that could come out of this clinical MRI scanner. But again, we want it to be a high field because why? We actually produce more signal that way. So if you remember back to the conversation of SNR, how high resolution we can reasonably acquire with MRI is related to the amount of signal available. If we increase this magnetic field strength, we'll have inherently more signal available, and that will be a motivation to go to higher fields. Or is it? See, this is again the challenge with all medical imaging and MRI in this case is when we do get higher field strengths, we also have more challenges. And one example is something called magnetic susceptibility, which is when you introduce certain types of materials into an MRI environment, they might have different dephasing interactions with other material types. So in this example, a non-ferromagnetic metal, a metal that is safe for an MRI scanner, can still interact with biological tissue nearby and cause dephasing of the signal, which leads to signal loss. So in this example here, someone has a hip implant, and the hip implant made out of titanium is perfectly safe for the scanner, but it does unfortunately completely destroy the signal that is close to the hip, which is probably the area of interest in the scan. It also will have effects at higher field strength of things called chemical shift artifacts, which is essentially when macromolecules like fat or lipid um, again cause slightly different resonance. That Lamar frequency is slightly different for the fat compared to water, and it'll cause those types of tissue in the body to have a shift and appear in almost the wrong location of the MRI image. And then, while generally implants that are put into people nowadays are non-ferromagnetic and generally MRI safe, they might only be approved conditionally for lower magnetic field strength. And so perhaps you might not be able to scan someone with, for example, a 7 Tesla MRI if they have certain type of implants. So maybe there are some challenges associated already we can imagine at the higher magnetic fields. But we do, in addition to getting more SNR, have, other benefits. So not just better imaging resolution, we also get better spectroscopic resolution. So if you remember spectroscopy measuring different metabolites in a spectrum of metabolites, in this case, the brain, when we go to higher field strengths and we have that higher frequency, that means our spectral bandwidth also improves. And so we can delineate and separate what could have been before overlapping metabolites, we can now separate them a bit better with the higher magnetic field. And just like when we had that challenge of the metal causing higher susceptibility or interference in the signal at higher fields, that susceptibility is also advantageous for things for like the functional MRI I talked about, because there's a bigger difference now between oxygenated blood that's maybe feeding some area of neuronal activity and deoxygenated blood. So, like I mentioned, we want probably a very high magnetic field, subject to a few caveats. And we have this idea of electromagnetism where if we have a coil of wire and we draw the current through it, we have a large number of turns, we can produce a large magnetic field. But there is a limit because at a certain point, the resistance overtakes that ability to create a very large magnetic field. So the way that we surpass that to get to the type of magnetic field we need for MRI is with the property of superconductivity. So with superconductivity, we need to lower the effective temperature of this whole electromagnet to almost absolute zero, and that pretty much dissolves us of this problem of resistance. And the way that we get it to absolute zero is MRI scanners use liquid helium, and we maintain, a temperature of about 0 Kelvin constantly through the scanner. So that's to say the MRI scanner is always at the magnetic field unless it's, been decommissioned. And that liquid helium is constantly being pumped and recirculated as it burns off and then being cooled down again to keep this superconductivity property. Um, Although there is a caveat because there are other types of MRI scanners that are available that use either a permanent magnet or a resistive magnet, which is the classic type of electromagnet I was talking about. But those types of MRI scanners are not as common, and they cannot get to what is the more usual clinical field strength of 1.5 Tesla or above. So you'll see those for specialty applications. For example, a lot of orthopedic imaging can make use of other types of MRI scanners with different magnet types. So I've talked to you a lot about magnets, and I'll only touch briefly upon the radio frequency field part. But it's just to say that to deliver the radio frequency field that will help cause those atomic nuclei to process and then generate the MRI signal, we often need a dedicated radio frequency coil. And this becomes more and more important when we get to stronger and stronger magnetic field types. But rather than touch upon this, I'm going to leave this topic to Dr. Shajan Ganumani following this because that is his area of expertise. So finally, the final portion of this whole system for the MRI hardware is the gradient coils, which will generate the gradient fields. So the gradient coils are also inside the bore of the magnet, and there's a nice pictogram on the right here that show you their orientation. So they're done such just to cause a linear shift in the magnetic field along the three spatial dimensions. So you have X, Y, and Z. You'll create these linear shifts, and we do this deliberately while imaging because then we'll be able to tag essentially different parts of the body so we can localize where the MRI signal is coming from. Otherwise, if we were to receive the signal of the spinning protons as they process, it would just be a mix and we couldn't be able to map where the signal came from to the spatial location of the body. So gradients are hugely important. But, gradients are also going to be the part of the scanner that really gives you the imaging performance because they have a certain strength of that linear shift that they can generate, and that's normally in the order of millitesla per meter. And then they also can only go so fast, and that's called their slew rate, which is done in the order of Tesla per meter per second. So the quality of the gradients is going to have a huge effect on the ability to scan fast in MRI, to give you a good resolution. And then it also has a large role in certain types of applications like that diffusion imaging that I mentioned earlier, which shows you the diffusivity along white matter tracks, for example, in the brain. Okay, and I wasn't sure if we were going to have a question, but please feel free if you have any questions. I'm happy to answer as we go. But I'll move on to now to the next part, which is talking about imaging parameters and contrast. This is a big whistle-stop tour and a lot of MRI and medical imaging concept, but I hope that I'm showing you the different pieces that we can use to generate an MRI image. So imaging parameters. Well, when we think about medical imaging, and again, we'll stick to looking at the brain right now, we typically orient an image along one of three planes. In reality, we have the advantage here in MRI that we can create a 3D image. But to visualize it here in this 2D presentation, we put it along one of three axes typically. So commonly we might see an axial slice like on the left-hand side. This is also called transverse. And here, basically, this is kind of the classic XY dimension of the brain. Then often for other applications, we might see a sagittal image of the brain. This is nice because you can see the coverage going down into the brainstem. You can see the cerebellum. This is along the Y and Z dimension. The Z dimension is typically the head foot dimension while the subject is in the scanner. And then also you can see the coronal slice here, which is kind of going, from the front of the face to the back of the head, the XZ dimension. We also, when we consider making an MRI image, we consider the field of view. The field of view is how much coverage we're going to extend when we do our data collection. And related to the field of view is also the resolution, and I'll explain why. So here I have my field of view, and I'm showing the field of view that I'm going to collect in the Y dimension. And in this example, it's adequately sampled, but if we don't extend our image when we want to do our data collection along a large enough field of view, if I take this Y dimension and I only acquire maybe the center of the brain, I won't just receive an image within the center of the brain. Unfortunately, I'll have signal coming from outside of the field of view wrapping in, and that's called aliasing, and we'll get something that looks like this if you don't do enough data collection. So again, to see how a field of view relates to your imaging resolution, we don't just need to extend an appropriate amount of field of view. We also need to collect at an appropriate weight. So we have to define a matrix size. And the resolution that we end up getting, then you can do the quick math to see is that it's the field of view divided by the matrix size that gives you your imaging resolution. Um, Typically, when I was talking about exciting the atomic nuclei with the radio frequency field, we thought about it as, taking all of the atomic nuclei and putting them perfectly perpendicular to the longitudinal magnetization. But to receive the signal, you actually don't need them to be fully all the way exactly perpendicular. They can be measured as their vector component onto the transverse plane. So the amount that you actually excite those spins away from the longitudinal dimension, that's called the flip angle. And we choose different flip angles for different types of contrasts and applications. And that should become a little bit more evident as we go. And then when we apply this radio frequency pulse for creating a radio frequency field, we cause the atomic nuclei to almost instantaneously get into their transverse plane away from the longitudinal one. But then we often wait a little bit of time before we actually start recording the signal. Again, for contrast reasons, we wait a little bit of time and we record the signal as they process slightly afterwards. And the amount of time that we wait is called the echo time. And the signal that we collected is called the echo. But really, signal could be recorded at any time after the RF pulse. Typically, the echo time itself is like on the order of milliseconds. It almost always has to be greater than whatever the T2 value is for the type of tissue that we're measuring, because if it's too much longer than T2, then the signal has mostly disappeared by the time we're measuring the echo. And then, to do this, we often collect data a single line at a time. And so we repeat this process. So we apply an RF pulse, we collect the data of the echo, and then we move our gradients. We apply another linear phase another linear frequency shift with our gradients, and then we acquire the data again. And each time we do that is called a repetition time. So it's this process of applying RF, collecting our data, and then after the appropriate amount of time for recovery, we wait for that we do the next RF pulse and we acquire the data again. So the repetition time, or the TR, is always going to be greater than the echo time, because echo time is, before you repeat the process again. The TR typically also is like in the order of milliseconds, can be in seconds as well. But we normally say it, in the thousands or hundreds or thousands of milliseconds. The TR itself, because we need that signal from the protons to come back up to the longitudinal magnetization, the TR is more often than not related to the T1 value of the tissues that we're trying to measure. So the TE has relationship to the T2 and the TR has relationship to the T1. So knowing this, we can play around with the timing of the TE and the TR to get different contrasts. That's why these concepts are important, because we'll get different looking images with different types of clinical value, changing the MRI physics just subtly. So here's the T1 weighted image. This one, you can really distinguish the different tissue types in the brain. So around the brain itself is this liquid, the cerebrospinal fluid, which is very important for protecting the brain. And in this case, it's that black area between the fat of the brain and the brain itself. There's also the skull there. The skull isn't visible because bone is very hard to image with MRI, not impossible, but it often doesn't show up in MRI images because has very little water content. So we have our CSF, which is that that very dark signal. We have the fat, which is just mostly on the top of the skin surrounding the head. So that's that very bright signal. And then we have gray matter, which is on the surface, the top cortex of the brain. That's the medium dark. And then inside the main tissue of the brain, inside is the white matter, which is medium light. And then if we kind of swap those contrasts, We then get what we call T2 weighted. So now we can see the CSF is super bright, and there's actually CSF in the center of the brain via the ventricles that we can see nice in this axial image. And then the gray matter and the white matter have also switched their colorings. So these are two different really common ways of viewing the brain, T1 versus T2 weighted. And they'll have different, diagnostic rationale behind both. But yeah, when I look at an image, I have enough familiarity that I already know what is T1, what is T2. But the clearest way to do it is to look at the CSF, look at where the fluid is. If CSF is dark, then it's T1, and if CSF is bright, it's T2. There's other contrast. There's also weighting of that T2 star, which is not just T2 weighting, but it also includes inhomogeneity factors. So this could be inhomogeneity of the main magnetic field. Maybe your scanner has, it needs some improvements, it needs some shimming, and it's slightly inhomogeneous. You might, get your signal distorted while you're scanning someone based on that. But in this case, it's actually used as an advantage because this T2 star contrast is actually capturing inhomogeneities introduced by deoxygenated blood in the venous system. So it's really helpful for venous imaging. And later I'll show you some applications of this T2 star weighted contrast. That's again, because of this inhomogeneity or susceptibility is known as susceptibility weighting. It's kind of the standard for imaging veins in the brain and in the body. There's also something called proton density contrast, where it's kind of finding that halfway between T1 and T2 weighting, and it actually doesn't relate to those relaxation times of the atomic nuclei, but actually the count of the protons in the different tissues. So you can see it's a little bit unique of a contrast here. The white matter is kind of the obvious thing to see here, with the white matter on the internal part of the brain, where you can see the different fiber networks and the kind of the connectivity of the brain there. So generally how we would kind of this is not done with specific values because it's going to be very dependent on a lot of things within an acquisition, but kind of more because of more like general speaking, we can put these sort of classifications into how we would get a T1 weighted image, how we would get a T2 weighted image, and a proton density image. So you can see with short TE, short TR, relatively, you will get a nice T1 weighted image. And then on the other side of the spectrum, with a long TE and a long TR, we'll get a T2 weighted image. So T2 weighted imagings are like are generally harder to acquire, but they still have like high clinical value. So you have to do a T2 weighted scan in a lot of neuroimaging patients. But you also see that in the bottom left corner, there is no type of contrast that exists for a long TE and a short TR. And that's because often it's not possible, as the TE always needs to be shorter than the TR. So there's not really a case where you would have a long TE and a short TR. Okay, so putting in those concepts of we have these different imaging parameters, well, what do we do to put them all together and actually make an image? We talked about the process of nuclear magnetic resonance. We've talked about how we build a scanner to make that signal. We now know different, parameters involved in that signal, and then this is everything together, and that's called an MRI pulse sequence. So basically, we want to know how do we time the RF pulse with the echo time, with collecting data, where does it all fit in? That's done through this sort of pulse sequence diagram here. So you can see it's really specific. Time is on the x-axis of where things occur and what are the reasons for doing each thing. Before I talked about those gradients as spatially localizing, we also can distinguish them based on which one for the given orientation we're collecting is doing certain tasks. Because data is collected actually in the frequency domain, we collect some data with frequency encoding, and then we also apply linear phases to the data to do phase encoding along 2 dimensions. And then the final dimension that we will collect data with is using what's called slice selection, and that's where we acquire 2D data in different slices. So MRI physicists love looking at these pulse sequence diagrams and coming up with clever new ones, but really there's two main types of pulse sequences that are really critical for MRI. So the first one is the gradient echo, and this is a really simple way of showing a gradient echo. It's the same figure as before. And basically, it requires just a single pulse for a radio frequency field. The flip angle, so the amount that you actually move the spins towards the transverse orthogonal plane is going to be up to 90 degrees. And then we're going to use gradients to time exactly when we want to collect the data at that echo. So basically, every TR only has one RF pulse and one time for collecting data. And then another type of pulse sequence that's equally important is the spin echo. And this one's slightly different because rather than having just a single RF pulse, we actually have two RF pulses that are a special pair called a spin echo pair. And those are defined to have first a 90-degree pulse and then a 180-degree pulse. And the timing of them are such that the distance between the 90-degree and the 180-degree is exactly half of our echo time. So between 90 and 180 might be 1 millisecond. And then after that, 1 millisecond more will be when we collect our data. Why do we do this? It's because actually this type of pair of RF pulses is really special. It actually eliminates any sensitivity to those susceptibility or inhomogeneities of the magnetic field, and it creates real T2 weighted images. And without spin echo, it'd be really hard to get pure T2, and we'd have mostly T2 star weighted images. This is another reason why when we're looking at how to build that type of contrast, we have long TE and long TR. It also has to do the fact that now we need to have two RF pulses and they have really specific timing that they're dictated by. Finally, after we have, in all of these scenarios, we have our RF pulse and then we have the point at which we're doing data acquisition. And in the data acquisition part, we have different ways of actually using our gradients to really quickly acquire that data. So at the echo time, you might think of just acquiring data line by line, and that's quite usual, but it's not really the most efficient way to collect data fast. So you could do data line by line in a Cartesian fashion shown here. Or you could be a little bit more creative and you can do things in a zigzag back and forth through every line phase. So every single time we collect an echo, we collect a full 2D slice, and that's called echo planar imaging. It's really popular. It's also known as EPI. Or if you wanted to do things subject to really specific, smoothly moving gradients, that kind of helps understand the actual velocities available to you. You might do a spiral image, but then that becomes a little bit tricky because then to generate the MRI image from the signal you received is a little bit less clear because it's not exactly a Cartesian readout. So what is the data itself? If you think about it, if we're receiving the precession of these spins in the magnetic field inside of a radio frequency coil, and it's having this sort of oscillating fashion in FID, it's a little bit of a disconnect between that FID signal and the MRI image we produce. And actually, when we receive the signal, we don't acquire it in time domain, we acquire it in the frequency domain. And it's actually a spatial frequency domain. So the spatial frequency domain looks like this, and it's something called k-space. And how you can think about it in terms of spatial frequencies is a lot of this like slowly moving bulk contrast of our image is in the center of this k-space plot here, because that's our low frequency data, and that's the majority of our image content. And then all the outside pieces of k-space, the high frequency data is the sparse things such as the edges between two different tissue types. So we have this k-space, and then it's really it's for me, it's very beautiful that the way that we can get to the actual MRI image is just simply through a nice inverse Fourier transform. So when we inverse Fourier transform this data that we've collected in the spatial domain or spatial frequency domain, then we can get it into the image domain quite readily. You'll notice though that I put an asterisk around inverse Fourier transform, and that's because that's what's been done, classically. But people have gotten a little bit more creative now. We've realized with time that we don't actually need to acquire all this data equally sampled and case based. We can undersample it and we can be a bit strategic about it. And then rather than imply simply the inverse Fourier transform, there are iterative optimization methods that you can use to reconstruct the image using less data, but still getting the same image quality. And of course, nowadays with deep learning, this is something that people do all the time through artificial intelligence methods. Rather than even use an optimization routine, they just feed it through a trained neural network, and then they can reconstruct a beautiful image with highly undersampled data, which will ultimately be of benefit clinically because you're scanning someone for less time. So now we kind of talked about how we generate MRI. I think we've given a very, high overview of producing MRI images. But for me, it's also important to think about the safety of an MRI scanner. In general, MRI is very safe. You can have as many MRI scans as you want, and you're not going to increase your risk of cancer. You're not subjected to ionizing radiation. This isn't the same thing with X-ray or CT or PET imaging. So, in our site, we very readily are volunteers for each other's scams. There isn't safety concerns there, but you do have to understand the physics very carefully and be diligent with the type of hardware you're working with. So the biggest thing, to consider with MRI safety is that this is a very, very strong magnet. It's, measured in field strengths of Tesla. When, we talk about Tesla, that's 10 to the fourth Gauss. And the main magnetic field of the Earth is, a few Gauss or less. So it's very, very strong magnet, even in relation to the strength of the Earth's magnetic field. And because of that, you always have to be wary of bringing any ferromagnetic materials. All things that are going into the MRI environment should have some sort of labeling stating whether they're acceptable to be there. Some are conditional, some are, absolutely not, and some are safe. So, in this example on the right, this is obviously something like a cart that was brought into the MRI scanner room that does have ferromagnetic materials in it and was not, approved for MRI. And it basically becomes a projectile as soon as it gets close enough to those fringe fields. It will just be projectile straight into the center of the magnet where the field is strongest, or as close as it can be to the center of the magnet. So, this is a huge accident and it's bad, but fortunately in this case, there is nobody inside the scanner. If somebody's inside the scanner, this can then very quickly become a deadly experience. So you have to be very, very careful. And often you see signage like on the left where it'll very clearly say that there is an MRI scanner beyond this room, and it is never not at the magnetic field. In addition to that, some types of internal electronic devices are not MRI compatible because their electronics themselves are affected by the main magnetic field. So a good example is an electronic pacemaker. I think a lot of pacemakers nowadays are being made to be, more compatible with MRI, but older editions not so much. So you would never want to get close to an MRI scanner if you had a pacemaker for your heart. But again, whenever someone is being brought into an MRI environment like this, there's always a pre-check before, just to really avoid any sort of complication, because you have to always be mindful of these things when using MRI. So what happens if you get something stuck inside the scanner, but the scanner is always on? What do you do? Well, if something gets stuck inside the scanner, it's tricky because you'll probably have to work with the scanner manufacturers and the engineers to try to remove it. But really you want to try to maintain the magnetic field because you're using all of that liquid helium, which is very expensive and one of the main costs of the MRI scanner. And so you really don't want to lose that scanner and the main magnetic field if possible. But in the case of a life or death, if someone was stuck to the scanner themselves because of a ferromagnetic projectile material, then there is an option called quenching the magnet or quenching the magnetic field. So in every MRI facility, there will be a button somewhere inside on the wall, big, a lot of signage for the emergency quench button. And this will be something that will essentially open a valve and allow all of the liquid helium to quickly burn off. And then the main magnet will lose its magnetic field strength in around 30 seconds. But you would never do this unless it's a life or death situation because it will pretty much decommission your magnet. So this could be potentially like on the order of $1 million or pounds or euro type decision. So yeah, it's to be avoided if possible, but sometimes people do it, when they have very, very old scanners that they're going to decommission on intentionally, they will actually quench it on purpose. And that's why you get videos like this where you can actually see it happen. Because, it is quite, you wouldn't really see this many times in your lifetime. Um, yeah, so the other issue that could be related to safety, or one of two other issues that could be related to safety with MRI is RF heating. So generally, we don't worry about ionizing radiation with MRI because it's all below, the wavelengths of the electromagnetic fields are all below the visible light spectrum. But with radio frequency pulses, when we apply them, continuously, we can contribute to heating in tissue. And we monitor that through MRI through something called the specific absorption rate. So that's, yeah, related to the electric field component of electromagnetic field. And the specific absorption rate is actually just like directly linked to temperature rise in the body. So tissue itself will absorb and be affected by radio frequency in a certain manner, but other things inside the body might be more conductive. So if you have, for example, an implant that even if it's non-ferromagnetic, it can be more conductive and more susceptible to RF heating. But people are also more aware and commonly know of tattoos being an issue with MRI. And also nowadays, permanent makeup can be of concern. So the way that the specific absorption rate or SAR is typically monitored in MRI is not just related to the amount of power that you deposit, but also, per unit time. So if you have more time, there's more dissipation of that heat, and so then you can apply RF again. And why you would apply so much RF is, it's going to be a function again of perhaps the contrast that you're trying to receive or the quickness of which you're applying your imaging and how fast you can scan. And then finally, this is kind of another part of MRI that people think about is how loud it is. And that those noises actually are coming from those gradients, those gradient coils that are switching and changing, the linear frequencies shifts of the field to change where we're acquiring the data from. We do those very quickly, and then that generates a lot of noise. And that at some point can become, to the level of hearing damage. And so every time that someone would go inside an MRI scanner, you'll always have some sort of noise protection to help alleviate that. And when they build scanners, there also is some understanding of what's the acoustic noise limits that are acceptable to someone. And then on top of that, it's really interesting because if you have these fast switching gradient fields while you're being scanned, those can actually induce small, currents inside your peripheral nervous system. So the nerves that are on the, peripheral parts of your body, like your limbs, and that actually could cause some twitching, which should be uncomfortable to someone. So the way that a lot of MRI sequences are designed have this in mind, and they limit the amount that you can move in certain ways with these gradients when you do data collection to also reduce the effects or chances of stimulating your peripheral nerves and causing some discomfort. It's not dangerous, but it can be discomforting to the patient. We want to try to alleviate that. Okay, so this is the final part of this series, and I'm going to turn our attention to something that's my particular area of research, and which is ultra-high field MRI. And this will be a really nice transition into your next lecture as well from Dr. Shajan Gunamani. The ultra high field MRI is just the category of the field strengths of MRI. So anything above 7 Tesla, which now there exists even higher field strengths, that would all be called ultra high field MRI. And this just comes because of the actual resonance frequency of 7 Tesla is categorized as an ultra high field frequency because it's 300, well, it's about 300 megahertz. So that's the cutoff for ultra high. And so that's where we got this name of ultra high field MRI. And in 2017, we actually saw, although 7 Tesla MRI has been around for more than a decade now, it wasn't until 2017 that it got approval for imaging by the European agencies and also the FDA in the US. And so now it's really gaining in popularity, not just for research, which was its main interest previously, but now also for clinical MRI, mostly imaging of the brain. So we have one at Glasgow, and it's also one of these CE FDA labeled ones. Um, I mentioned that there's beyond 7 Tesla MRI, and I had the great opportunity to visit the world's strongest MRI scanner a few years ago. So this is the 11.7 Tesla or 500 megahertz scanner in Paris. At the moment when I was in this image, it was actually not at field strength, which is why I was able to get so close. But the curious thing about this scanner is that it looks quite big, like it's taking up the whole room, but that's not even the whole scanner. The entire magnet with all of the wirings to get it to superconductivity is actually taking the room above it and the room below it. So the magnet is kind of 3 levels large, and the bore of it is 6 meters. So once you're inside it, you still have a lot of space from your feet and your head. But what, they did their first scans of human beings last year, and the way that they publicized it was actually Emmanuel Macron, the president himself, posted this tweet about it. So that was quite exciting for them to, after all the work of building the strongest scanner, to finally have the first human images. And what you get from it is just really incredible resolution of the brain. So essentially, what are these exact effects of ultra high field? I already mentioned you get more SNR, and that SNR just goes up, not even just proportionally, but even beyond proportionally, exponentially with field strength. It also does affect any susceptibility to inhomogeneities in the main magnetic field. So that will scale with field strength. And then the ability of different resonances of fat and tissue, those chemical shift artifacts do unfortunately also increase with field strength. When you're applying radio frequency pulses, the amount of power that you deposit, unfortunately, again, scales with field strength. And then because we're operating at a higher frequency, inversely, that means we have a shorter radio frequency field strength. So that gets smaller. And then those relaxation times like T1 or T2, T2 star, those are also changing with field strength. So a lot of things means you have to do imaging completely different at a different field strength. So here's a really clear example of why SNR increases. So these are showing ratios between 3 Tesla and 7 Tesla, and then 7 Tesla and 9.4. And you really just see like the peripheral part of the brain in these figures, just the SNR just skyrockets when you get to higher field strengths. And then also importantly, the difference between 7 Tesla and 3T is almost factor 4 in some areas of the brain in terms of SNR. So it's very impressive. Means you can do much higher imaging and potentially at a lower scan time, but that is slightly affected by the changes in relaxation here. So it's not just an easy calculation because the relaxation of T1, the amount of time it takes for those spins to recover to the main magnetic field, that actually increases at ultra high fields from lower field strengths. And then the value are the T2 times, so the time of dephasing between those spins individually, that actually decreases. So you have kind of this opposite effect with T1 and T2 with field strength. There's also this concept called parallel imaging, which is related to when I talked about undersampling of data to be able to scan faster. Typically, the amount that you can undersample might be related to the using sort of an array of receiving coils to collect the data. If you have some redundancy by collecting with multiple coils in an array, maybe you can undersample a little bit more strategically. That seemed to be previously the main, driver behind parallel imaging. But not only do you get more SNR with higher field strengths, you also have some interesting geometry factors that allow you to do more parallel imaging. So you get to maybe reduce scan time in two reasons because of improved SNR and also improved parallel imaging benefits. But, not everything comes for free, and that's certainly the case again with medical imaging. So there are a few challenges. Like I mentioned, there's this problem of susceptibility that becomes worse with ultra high field. And that makes it more likely that you're going to have interactions when you have two different tissue types, or, for example, metal and tissue. On top of that, when you're applying these radio frequency pulses necessary to generate the signal, the amount of power that's being absorbed by the tissue that's related to heat will also increase when you increase the magnetic field strength. So if you put those first 2 points together, it means that at ultra high field, it's very hard to scan patients with medical implants or devices. So in this figure here, it's actually showing you this simulation study because in neuroimaging patients, a lot of times they've had previous surgeries. And when you operate on the skull afterwards, you often have clips in the skull. And those clips can become problematic at ultra high field, which is really not great because you have a lot of interest in scanning these patients at ultra high field. So it requires really careful studying of what are the conditions of heating with these type of devices, with these implants. So in the case of this clip, if you look at this small cutout, yes, you can see there is increased heating associated with this clip. However, if you look at the color bar, the amount of heating relative to none is still quite minimal. It's at most maybe like 0.3, 0.4 degrees Celsius. So that's quite within an acceptable range. And when you go out to like the larger scale view of the brain, you can see that in reality, this clip is not affecting the overall temperature change in the brain greatly. And so in this case, this would be an acceptable device or implant for scanning at ultra high field. But unfortunately, that cannot be said about a lot of things yet. And it's because of the risk associated, it's a slow moving process to find ways to mitigate this and to gain more approval and consensus for scanning these type of implants and devices. On top of that, we do have this decreased RF wavelength with the higher frequency. And that actually makes the whole field for which we're generating our signal, generating the spins that are going to, precess and create our MRI signal, that whole RF field is getting less and less homogeneous. And this is a really nice example that I think Shajan will show again, that at 3 Tesla, we have a wavelength around 26 centimeters, which means that 26 centimeters will pretty nicely cover the full diameter of the human head. And then at that sort of level, we can image the brain relatively well without any, interference of the wavelength, any central brightening, any darkening of areas of the brain. But at 7 Tesla, unfortunately, the wavelength is quite low. It's 11 centimeters. And then we start to have these interference effects in the brain. So the way that we can mitigate some of these problems is with something called parallel transmission. And essentially, it's the process of applying multiple transmit fields through a dedicated RF coil that allows us to shape the deposition of this radio frequency field in such a way that we can come back to a more uniform excitation and also mitigate the power deposition while we're doing it. So this is just a nice GIF that's showing you 8 parallel transmit channels measured in vivo. These are radio frequency fields measured in Tesla per volt, but they have both magnitude and phase. And then when we put them together carefully, we can show each of their contributions, or in summation, where we'll generate a very uniform flip angle. So the way that we do this is one of the really wonderful things that Shajan does himself, and it's through dedicated parallel transmit coils, and they have a very unique hardware solution to independently generate these radio frequency fields. We have to be a little bit mindful of safety, particularly with parallel transmission, because we do have these larger degrees of freedom to generate the radio frequency field. They are also on top of that overlapping. And so if we're not mindful, we can unintentionally create local hotspots. So it's really important to be aware of the electric fields that we generate with parallel transmission. And because we can only measure magnetic fields and not the electric fields during an MRI scan, we corroborate a lot of the work we do with parallel transmission with realistic body model simulations. So in this figure on the left, we're showing what is the simulation of the full body, and then which is quite computationally expensive. It's a lot of Maxwell equation solutions being solved in a GPU. But on the right, it's showing the same simulation, only reduced over the spread of the head. And fortunately, in this case, we can see that we don't need to extend our simulation quite so long in the body, and we can save on computation time. Okay, so those are some of the challenges. Fortunately, parallel transmission is a great solution to address it at ultra high field. So let's close today looking at some beautiful applications of ultra high field, and we're going to look at it for clinical neuroimaging. So here's another really nice T2 weighted image, and it's collected at 7T. And you can tell that because of the resolution. If you're familiar with MRI, it's very high resolution for a T2 weighted image. And on top of that, you can really see what are the different components of the brain. You can tell where the CSF is. You can see very clear delineation of gray and white matter. So this is kind of like the high standard for like clinical neuroimaging that any neuroradiologist would want, is what some image like this that you could get with 7T. And then it has real clinical benefits too. So this is an epilepsy patient example, and a lot of these clinical examples are from our really close collaborator, Professor Natasha Fullerton, who's a clinical neuroradiologist in NHS Greater Glasgow and Clyde. So this is one of her epilepsy patients. In this case, they already knew about the lesion area of the epilepsy from 3T. Sometimes you can't actually identify these on 3T, but you can see the heterotopia here on the left, but you cannot see the boundaries very well. And if you wanted to operate on it, it would be much more beneficial to have the 7 Tesla MRI to really see these tissue boundaries. And this is the same patient again with a different contrast. So you can again see very clearly, oh, this is gray matter heterotopia because it's infiltrated the white matter. This is a very clear lesion source or lesion and source of epilepsy in this patient. Another really great example I mentioned previously was MR angiography. You can really see high resolution extent of the arterial system in the brain, and you don't need a contrast agent. And then on top of that, you don't really, need to use ionizing radiation as a corroborating factor. You don't need to use something like fluoroscopy, which is the clinical standard. Not only are we benefiting from the high resolution that we're afforded from MRI, in this particular type of MRI sequence, it's better if you have long T1 values because it allows you to suppress all the signal that's not flowing blood. And so in our case, we have longer T1s at ultra high field. So it just makes the arterial system stand out even better for this type of contrast. And so in this example, on the top, we see the MR angiography, and on the bottom is the X-ray fluoroscopy equivalent. So that's the ionizing radiation, which is the standard. And the nice thing about that is you get really high resolution, but we get it just as well with MRI at ultra high field. This is another complementary example. Now this is with the venous system and the susceptibility weighted imaging. Like I mentioned previously, the veins have deoxygenated blood, which will perturb the main magnetic field. And in this case, we use it to our advantage because then we can see, where the veins are located in the brain with a particular type of imaging acquisition. In this case, we're showing 3 Tesla on the top and 7 Tesla on the bottom of the same patient. Right away, you can see, wow, I get so many more small veins in the 7 Tesla image. But what's really nice is if you look at the zoom, you can really see this sort of infarct that is only smiley visible on the 3 Tesla image, but has really great visualization on the 7 Tesla image. And then finally, we'll show this example from spectroscopy. This is now in a tumor patient. And spectroscopy is really useful there because the metabolic information of tumors can be beneficial during treatment of brain tumors because as a tumor hopefully responds to some sort of radiation or chemotherapy, it might return its metabolic activity to be more similar to healthy brain tissue. So typically what you do is you don't just acquire spectroscopy or a spectrum in a single voxel, you might acquire it in the tumor and then also in healthy tissue. So here on the top, we have the healthy tissue, and then on the same on the same region of the brain, but on the contralateral side. And then on the bottom, we show the tissue of the tumor. We don't have the metabolites exactly mapped out on the frequency band or the x-axis, but you can see very clearly there's a huge difference in the metabolic profile of the tumor compared to the healthy tissue. And it's sort of this sort of delineation of all these metabolites you can't easily do at lower field strengths because when the frequency decreases, the bandwidth also does. And so therefore, we have more overlap on these metabolites. Again, I talked about this parallel imaging capability that we're afforded with ultra high field. So it really complements the high resolution that we get with ultra high field because when we have that really high resolution from the SNR or high SNR and then higher resolution, we could take a very long time scanning. So on the left, we show this really nice MRI again, but what you don't know is that that's actually taking over 12 minutes. And 12 minutes is a really long time in a single scan, which we'll probably have multiple in the same session. And it's a long time for one sequence for the patient to stay really, really still because, this is maybe 0.2 millimeter resolution. So even if they move just a tiny bit, it's going to cause blurring over only 0.2 millimeter voxels. So when you use parallel imaging and like an advanced, data acquisition reconstruction called compressed sensing, you can actually reduce that scan time by third down to 4 minutes, which is a much more acceptable scan time for a lot of patients. So there's kind of two areas that are really promising for ultra high field, but still are quite challenging, the technical aspects in an area of interest for mine. So one is arterial spin labeling ASL, which is, at lower field strengths is hard because it's really a low SNR type of contrast, but it's important because it tells you about perfusion in the brain in a quantitative fashion. So it's not just related to the general contrast of tissues, it actually has a measurement for brain perfusion. So for things like stroke, it's absolutely essential. And then it also really benefits from the so-called background suppression again. So when you have long T1s, it's better as well. So you would think that with ultra high field, we'd really benefit with ASL, but unfortunately, it's also very high. It's highly associated with high power deposition or that tissue heating specific absorption rate. And then also it really needs a homogeneous radio frequency field. So this is a very exciting area where parallel transmission will have a huge impact. And likewise, it will also have a huge impact in diffusion weighted imaging because diffusion itself also really needs high SNR to be able to do this sort of tractography where you can measure different diffusion directions and white matter tracks. But diffusion is a T2 measurement sequence, and it's challenging because when we go to ultra high field, the T2 gets even shorter. So we essentially have less time to collect the data. And again, to get that T2 weighted data, we need to use the spin echo type of sequence, which if you remember was 2 RF pulses, and they were quite high RF pulses with a 90-degree pulse and a 180-degree pulse. And in conjunction, getting those type of RF pulses in a short amount of time means that we are depositing a lot of power. And so again, we have this question of specific absorption rate. But it's an exciting area again for parallel transmission to combat. So I'm going to leave us there today, just having you think a little bit about MRI and the many uses that it has, particularly in brain imaging, and maybe excited about some of the physics opportunities thereof. And I really hope that you enjoy the next lecture as well. That'll touch a little bit more upon this from Dr. Shajan Gunamani. I also I don't know if it's possible, but I can try to make these slides available to you. And I have some references here that might help if you have further reading. But of course, please don't hesitate to also contact me here and I'd be happy to help you. So thank you.
Thank you so much, ma'am. Can I conclude it?
Yes, yeah. I think there's a question. Someone has their hand raised. I'd be happy to answer.
Madam,
Yes.
so what are the future research opportunities in MRI?
Oh, there are so many. So pretty soon in May, we have the annual International Society for Magnetic Resonance in Medicine. It's quite a large society, maybe on the order of 10,000. And at the annual conference, maybe about 3,000 to 5,000 people will attend. And there it'll be researchers from around the world, mostly MRI physicists and engineers, discussing the exact research areas for the future of MRI. So what I would encourage you to do is to look, I'll put it in the chat. So the society website I'll put into the chat, ismrm.org. So there they have a lot of materials about different areas of active research. In our specific area of ultra high field MRI, it's probably most linked to how do we translate this technical work to clinical use. Because, you know, like I said, this ultra high field MRI has been around for over a decade, but it's mostly used by researchers and mostly people with MR physics experience. Clinicians aren't quite as familiar with it because it has technical challenges typically, but they're becoming improved. And then also, you know, changes in the image contrast, radiologists might not be used to. But as we're doing more clinical studies and as people like myself are working on easier solutions, it's making its way towards more clinical translation. There was the biggest need for neuroimaging, and it seemed to be the best way to go for ultra high field. But I also think there will be a lot of people looking at how we can use this ultra high field in other parts of the body. So in Glasgow, we've mostly been imaging in the head, but now we'll be starting to image more into the spine, especially the cervical spine attached to the head next to the brainstem. And then we've also gone and built a coil for pelvic imaging because prostate imaging is a huge benefit, or it's a huge area of benefit that MRI can provide. So at ultra high field, it might offer even more. But the way that we've been imaging is also not just exclusively for prostate. It could have other pelvic applications, especially for females as well, like uterine imaging. I think those are really big areas for MRI research in my particular interest, but again, it's a massive area. So if you're interested in any sort of topic, please look on the educational materials at ISMRM.
Okay, thank you, madam.
Shiny, I don't know if you had a question. Your hand is raised. Maybe not. Okay. Well, I thank you everyone for coming today. I'll put my email again in the chat. Please don't hesitate to write if you have any additional questions. And it was my pleasure again today. I wish I could stay for Shajan's talk, but I actually have to teach another class after this. Otherwise, I would love to stay. I've gotten to see him speak before this because we met to make sure that our slides were congruent. But he's a really great researcher as well, and he'll have a lot of interesting things to talk about with radio frequency coils. So I hope you enjoy that. And thanks very much. I'll hopefully see you guys around in the field of MRI research. Thank you.
Thank you, ma'am. As we conclude this Enrich Adult Faculty Development Program session, I would like to take a moment to express my heartfelt gratitude. First and foremost, I would like to extend my sincere thanks to our esteemed resource person, Dr. Sydney Williams, for the invaluable contributions. Our session was not only informative, but also deeply inspiring, and we are grateful for the knowledge and insight for you shared. I would also like to thank the management and organization committee of Marthandam College of Engineering and Technology for the tireless efforts in planning and execute this FDP program. Your dedication for academic excellence and professional development is commendable. Thank you all the participants. Thank you for your active engagement and enthusiastic throughout the program. Your participation and willingness to learn made this FDP truly collaborative and rewarding experience. Thank you once again.
Good evening, everyone. A pleasant evening to
Dr. Shahjan, are you ready?
Can you hear me okay?
Yeah. Yes. Okay, fine.
Good evening, everyone. A pleasant evening to one and all gathered here. I'm very glad to welcome you all to this section. It's my honor to introduce today's distinguished resource person, Dr. Shahjan Gunamani, an expert in the field of MRI radio frequency, coil design, and a pioneer in ultra-high field MRI technology. Dr. Shahjan Gunamani is currently the head of MRI radio frequency engineering at the Imaging Center of Excellence, University of Glasgow, where he plays a crucial role in advancing cutting-edge MRI technology. With an impressive career spanning research, industry, and innovation, his contributions have significantly impacted neuroscience and medical imaging worldwide. His expertise lies in developing high-performance radiofrequency coils for ultra-high field MRI scanners, devices that are now used in leading neuroscience research centers across the globe. He has also demonstrated his entrepreneurial spirit as the founder of Yamaha Coil Technic Limited, a Glasgow-based company that specializes in custom design 7 Tesla MRI head coils for research institutes and scanner manufacturers. Dr. Shahjan Gunamani holds a PhD with Summa Cum Laude from the University of Tübingen, Germany, where he focused on radio frequency coil technology for ultra-high field MRI. His academic journey began with a master's in communication system engineering from Madurai Kamaraj University and a bachelor's in electronics and communication engineering from Baghdad University, India. Throughout his career, he has held significant positions, including as a senior research fellow at the University of Glasgow, a research scientist at the Max Planck Institute for Biological Cybernetics in Germany, and roles at GE Healthcare Technologies and the Indian Space Research Organization. His groundbreaking work has earned him 4 US patents, underscoring his contributions to medical imaging technology. Dr. Gunamani's research interest includes parallel transit array technology for ultra-high field MRI, high density receive arrays for functional MRI at mesoscale resolution, novel RF coils designed for scanners with high performance gradients. Beyond research, he has also played a key role in 12 plus innovative funded projects further advancing MRI technologies. It is a privilege to have such a distinguished expert with us today. Please join me in welcoming Dr. Shahjan Gunamani. I welcome you, sir. Now, I am handing this section to our resource person, Dr. Shahjan Gunamani. Sir, please take over this section.
Okay. Oops. Okay. Can you hear me all right?
Yes, sir.
Yeah, okay. Yeah. So thank you. Thank you for the introduction and good evening, everyone. I want to thank the organizers for inviting me. It's an honor and a privilege for me to participate in this seminar series and talk a bit about my research, which is on the design of radio frequency coils for ultra-high field MRI. I also want to thank the participants who are, it's already late for you, so thank you for staying so late to attend this seminar. So before I start, I want to give a brief introduction to my background. I started my career at the ISRO Satellite Center in Bangalore, where I was designing K-band amplifiers for direct-to-home satellite applications. So this was in the frequency range of about 11 to 12 gigahertz. And a few years later, I moved to GE Medical Systems in Bangalore, where I continued to work on RF circuit design, but this time for MRI applications. And also this was in the frequency range of about 100 megahertz, which is very much different from the frequency where I was working at ISRO. And then a few years later, I moved to the Max Planck Institute in Germany, where I was responsible for design of RF electronics and RF coils for ultra-high field MRI applications. This was my my first my job in an active research career. And the lab at MPI, we have a 9.40 MRI scanner. It was at that time the world's strongest human MRI scanner. And since 2016, I am now working at the University of Glasgow, where I lead the MRI RF engineering group. And as you heard in the introduction, a few years ago, I started this company MR Coiltech Limited, which is again based in Bangalore, in Glasgow. And we design and manufacture coils for MRI applications. So at the University of Glasgow, we are based in a center called the Imaging Center of Excellence. It's commonly known as the ICE building. And at any point in time, we have quite a few coil projects going on in parallel. We can put them in three different categories. The first one, obviously, is the coils for the University of Glasgow. Here we can see a list of different coils for different anatomies and under different stages of development. And we also collaborate with external groups. These are typically common grant-funded projects. We usually apply for collaborative grants, and then we have common projects together. The one such example is a collaboration with a group in Paris. They're called Neurospin. You already saw this 11.70 scanner in Sydney's presentation. That's currently the world's strongest human MRI scanner. It's 11.70 scanner. And our common project is called the Aroma project, and this is funded by a Horizon 2020 grant from the European Commission. So we have built coils for this scanner. So you can see one of the coils that we have built. This is for 11.7 Tesla head coil. And we are also heavily involved in the ultra high field national facility, which is coming up at the University of Nottingham. So we have a 30 million funding together for this 11.70 scanner, and it's currently estimated to be operational in about 2 years' time. So the coils for this scanner would be developed in Glasgow. And the company MR Coiltech is also in the same building. So when we started the company a few years ago, we were mostly doing contract research work. These are like one-off coils that are customized to meet the specific requirements of the different research groups. We are currently doing less of these kind of one-off customized coils because we have a close industry collaboration with partners such as Siemens and Canon, and we are into dissemination of the 70 head coils that we designed at the University of Glasgow, and we are currently into serial production of these head coils. So I'll talk a bit about this later in the seminar. So for today's seminar, I've chosen three topics. I start with an introduction to RF coils, and then I talk about the design of coils for ultra-high field MRI, and my last topic is about a case study on the commercialization of academic research. Okay, so I'll start with the introduction to radio frequency coils. So what exactly is an RF coil? If you have been to an MRI scan, you would notice that the nurse or the radiographer, they attach a device around the anatomy that they are planning to scan. So this device is basically an RF coil. It's an accessory, but it is an essential accessory because without an RF coil, you don't get an image. It's also the front end of the imaging chain, and it's really the first component that picks up the signal from the anatomy. So the quality of the RF coil, it largely determines the quality of the image. And the coils must be anatomy specific for optimum performance. You have to have anatomy specific coils. So here in the photographs here, you can see a list of coils. On the left, this is a general purpose flex coil, which can be wrapped around any anatomy of interest, but the image quality may not be the optimum. Here, this is a head coil from Siemens, and this is a coil for the ankle, and it's a coil for the knee. So these are, anatomy-specific coils. When we okay, so in an MRI scanner, there is a transmit coil and a receive coil, and as you heard, there is a strong magnetic field, and this is called the B0 field. It's always acting along the bore of the magnet. And when we place the human body in the magnetic field, the spins, the atomic nuclei, the spins of the atomic nuclei, it aligns with respect to this main magnetic field. And this is called the equilibrium position. And the field produced by the coil, it's always orthogonal to the B0 field. And this is called the B1 field. So there is a transmit coil. We apply high power on the transmit coil, and this will then flip the spins from the equilibrium position. So this is the function of the transmit coil. A receive coil is exactly reciprocal to the transmit coil. It works on the principle of Faraday's laws of induction. So basically, we have the spins that is processing in the magnetic field. So we have this oscillating magnetic field which induces a current in a neighboring conductor. So in this case, this neighboring conductor is the receive coil, and the signal induced in this receive coil is the MR signal, which we then amplify and which is then digitized and processed, and then we get the MR image. So we typically use a separate transmit coil and separate receive coil. In some cases, we use the same coil to transmit and receive, and these are called transceiver coils. So in this example I showed earlier, there is a transmit coil hidden behind the magnet bore, and these are all receive coils. So in this case, we have a separate transmit coil and a separate receive coil. And coils are made of resonance circuits. So this is the simplest form of a resonance circuit, where you have an inductor and a capacitor in parallel, and there's also a small resistance. And the coils these resonance circuits are tuned to the Lama frequency, and this Lama frequency is basically it's a function of the gyromagnetic ratio, that is the precision frequency of the atomic nuclei, and the main magnetic field. So if you have a 1 Tesla scanner, then for the hydrogen proton, the resonance frequency would be 42.58 megahertz. So as I said earlier, the field produced by the coil will always be perpendicular to the main magnetic field. And for a transmit coil, we expect the field produced to be homogeneous. The transmit coils are also called as volume coils because they surround the volume of they surround the anatomy. As the name suggests, they are called volume coils. And as you can see in these photographs, they are symmetric structures. So we can apply a current which is uniformly distributed in this structure. So because the current is uniform, then it produces a homogeneous magnetic field. And it's also important to have a homogeneous magnetic field because then you produce a uniform contrast across the image for the same tissue type. And there are two types of volume coils. These are called TEM coils and birdcage coils. And the TEM coils are made of transmission lines, and they are typically used at high frequencies. And the most commonly used volume coil is called a birdcage coil because the structure really looks like a birdcage. And there are three different types of birdcage coils. They are called low pass, high pass, and band pass. In a low pass birdcage, you have an inductor in series and the capacitor is in shunt, just like a low pass filter. In a high pass birdcage, you have a capacitor in series and then an inductor in shunt, just like a high pass filter. And then the band pass birdcage is a combination of the two. So the circular structure at the top, this is called an end ring, and then these straight structures are called rungs. So here you can see a low pass bird cage. And if you measure the frequency response of this bird cage, you would get something like this. So suppose we have a a coil with n rungs, you would measure n minus 1 modes. That means if you have if you have a bird cage with 8 rungs, you will measure 7 modes. Modes in the sense they are all these frequency peaks. And for a low pass bird cage, we want to the most interesting for us is the lowest frequency. That's called the uniform mode, where we produce a uniform magnetic field. So if you want to build a coil for low frequency, then you have to choose a low pass bird cage because the uniform mode is the lowest frequency. So if in the same way, if you want to build a coil for high frequency, then we have to choose a high pass bird cage because the uniform mode is the highest frequency. And here, this is an equivalent circuit of a birdcage coil. So it's made of inductor in series and then a capacitor in shunt. So here you can see this is a contour plot of the field produced by this birdcage structure. As I said, it has uniform current, so it will produce a uniform field, as you can see here. So here are some examples of birdcage coils. In the middle, these are body coils. These are fairly large structures. They're about 80 to 90 centimeters in diameter and about 1.5 meters in long. So these are typically hidden behind the magnet board, and it's behind the cover of the magnet. You don't see them outside. And the head coil it's much smaller. It's for imaging the brain. And a birdcage coil, it has 2 orthogonal modes. Suppose you have a coil which is horizontal like this, it produces a field vertically to the plane of the coil. This also means that we pick up the MR signal from the vertical direction. So if you have a coil oriented vertically, then it produces a field in the horizontal direction. And it also means that we pick up the MR signal from the horizontal direction. So this is called linear polarization. If you have these 2 coils operating together, that means we have these 2 coils in orthogonal directions next to each other, then we pick up the signal from 2 directions or 2 orthogonal directions, or we excite the signal in 2 directions. So this is called circular polarization. So I'm always talking about excitation and reception because it's also about transmit and receive. And they are always reciprocal. So this the block diagram on the right, it shows the setup that we require to set up this kind of circular polarization. So in an MRI scanner, you have a amplifier which produces a very high RF power. The output from this amplifier is then fed to a quadrature hybrid. The function of the quadrature hybrid circuit is that it splits the power into 2 outputs, which is minus 3 dB. But the 2 outputs will have a phase difference of 90 degrees. So these 2 outputs are then given to a birdcage coil at 90 degrees apart. So then we set up this kind of a circular polarization and we get a homogeneous image like this. So as you can see here, this reference is from the 1980s. So this is how the early MRI scanners were functioning. So we have a large birdcage coil that is used for imaging the whole body. They use smaller birdcage coils to image the brain. So everything changed in the 1990s with this introduction of the NMR phased array technique. This was introduced by Pete Romer, who was an engineer at GE at that time. And this revolutionized the whole MRI world. This is the only paper he wrote and in his whole career. And this has more than 3,000 citations. And every current MRI scanner currently uses this his NMR phased array technique. So he proposed a method to simultaneously acquire data from a multiple of small receive coils and combine this data into a single image. And this way you get much more SNR than a birdcage coil. And his concept that he introduced is very similar to a phased array radar, and hence he named it as an NMR phased array. So here you have the birdcage coils, as I showed you earlier. So there's a large and small. So because the body coil is quite large, the sensitivity of this coil would be very weak because it's a large coil. But it is a flat response because it has a homogeneous field. Similarly, a head coil is smaller, so the sensitivity will be higher. Again, it will be a flat response because it has a homogeneous field. If you now use a small surface coil closer to the anatomy, then it will have a much stronger sensitivity, but the penetration would be poor because it's a small coil, and it drops off quickly as you go away from the coil. So the NMR phased array technique basically uses this region where it takes a sensitivity of the high sensitivity of a small coil, and that sensitivity is then spread across a larger volume. This way you then generate an image with a much higher signal to noise ratio. So this is basically the essence of the NMR phased array. So here you can see this is a phantom in the middle, and you have 8 coils around this phantom. So let's say you have only one of this coil here. Then you produce an image like this where it is the signal is very strong next to the coil, and it falls off when you go away from the coil, as you see in this plot here. But instead, if you now have 8 of these coils surrounding this phantom, then you spread the sensitivity or you carry over the advantage of one coil to the whole volume. And then you get an image with a much higher sensitivity. So then the signal from these coils are then amplified, which are then down converted and mixed and so on, and then it is digitized, and then we get a combined signal. So in this plot here, you can see the sensitivities of the individual coils, and then the combined sensitivity, which is higher than the individual sensitivities. So Romer also proposed a method to build these kind of coils. So as I said, the coils are all resonant circuits. They are tuned to the Lama frequency. Suppose we have 2 coils. They are tuned to the same frequency. And if you bring them together, they're going to couple very strongly because of mutual inductance. And it will create a split resonance. And at the Lama frequency, you will have very low signal because the sensitivity is very poor, and the peaks are split. But you can overlap these loops to a point called critical overlap, at which the mutual inductance is 0. So then you get away from this split resonance and you create a single resonance. So in this example, you can see there are 4 loops. They are overlapped using this method. So the combined image will have a higher sensitivity, which is spread over a larger volume. So these are then connected to preamplifiers, and then that amplifies because the MR signal is really, really weak, and so you need to amplify this signal before they are down converted and then digitized. So if you geometrically overlap the loops, then they have to be adjacent to each other. Romer also proposed a method to decouple non-neighboring channels. So in this case, for example, A and C. A and B are neighboring channels, so you can overlap them. But what about A and C? So this method is called preamplifier decoupling. So in MRI, we always use low input impedance preamplifiers, which has a resistance of about 1 to 1.5 ohms. So this is the equivalent circuit of a coil, and this is the input circuit, which is at RF. This is called a matching circuit. So this capacitor C2 and L2, they form a matching circuit. So when you look into this coil from this plane, you see an impedance of 50 ohms, which is the characteristic impedance at which the noise figure of this preamp is minimum. Okay. But if you look into coil 2 from coil 1, what happens is that you have capacitor C2 and L2, and then you have this 1 ohm impedance from this preamplifier, which forms a resonance circuit. So at resonance, the property of a parallel resonance circuit is that at resonance, it creates a high impedance. So across C2, it creates a high impedance. That's what the coil 1 sees. So then because there is a high impedance, you create this kind of a response. That means when there is high impedance, there is low current. Okay, so then you have low current at that frequency. That way, coil A and coil C doesn't see each other. So this is the technique he used to, and this is called preamplifier decoupling because we are essentially using the low input impedance of the preamplifier. So this is the technique to decouple non-neighboring channels. Okay, so this is the coil he presented in his paper. This is a 4-channel coil, and he connected them to four low impedance preamplifiers. And this is the image from each of these coil elements. So you have 4 of them. This is the image of the human spine. Okay, and this is the combined image, where you get one image of the entire spine of the human body, but with a much higher sensitivity. Okay. So I also mentioned about a transmit coil and a receive coil, and they're all tuned to the same frequency. And the receive coil is in the field of the field of view of the transmit coil. So if you are transmitting high RF power, when there is another coil in the field, it will induce a lot of current, and this can heat up the human tissue, and it's a safety issue. So we have to switch off one coil when the other coil is operating. Okay, so this is a process called active detuning. So let's say this is an equivalent circuit of a receive coil. You have capacitor C and an inductor L. The values are adjusted such that they are in resonance. Okay, so if you turn on this diode, this capacitor C and L will become parallel. And as I said, this would then create a high impedance. So that is the blue curve. Okay, so when we want to turn off this, let's say this is a receive coil. So if you want to turn off this coil, you turn on this diode. So you switch off this coil, and the red curve shows the response when it is resonant. Okay, that means when this diode is off, this receive coil, that's called the tuned state. So it's in resonance. When we want to switch it off, you just turn on this diode. So this is, and the same thing happens in the transmit coil as well. So when we are transmitting, we switch off the receive coil. Similarly, when we are receiving, we switch off the transmit coil. So this process is called active detuning. Right. So now, once he introduced this NMR phased array approach, there are several coils now. And there for every different anatomy, and every coil is an array coil. This is a 32-channel head coil that was proposed by Graham Wiggins. So basically what he did was he took a helmet and he drew hexagonal and pentagonal patterns on the surface of the helmet, just like how we see in a soccer ball. And then he joined the vertices of these with these polygons, and you get circular loops, which are then overlapped. So then he created a 32-channel array coil like this. So here you can see the image from each of these 32 individual elements. And now you can see the SNR that you get from this coil. In the bottom row, you see the SNR of a birdcage coil. Yeah, it will be quite low, but it is quite flat, right? Because it always produces a very homogeneous field. In the middle row, you see the SNR profile of an 8-channel coil. And on the top, you see the SNR profile of a 32-channel coil. You get so much more signal with this one in the periphery and also in the center. So that's really the advantage of high channel count coils. These kind of 32-channel head coils have been really the workhorse coils in the MRI scanner over the last 20 years. And every vendor, like GE, Siemens, and Philips, they have their own version of these head coils. And these are 2 images from this coil from Graham Wiggins. So this is a very high resolution image in a sagittal plane. And Sydney also spoke about accelerated imaging or parallel imaging. You can accelerate the image acquisition. For that, you need high channel count receiver arrays. So this is an image with a 12-fold acceleration with with an isotropic resolution of 1 millimeter, and this was acquired in 1 minute 20 seconds. For this, you really need a high channel count coil. Again, a little bit more about this parallel imaging. So when we accelerate the image acquisition, you always lose SNR. Okay, so it is given by this relation. The R is the acceleration factor. So suppose you accelerate by a factor of 2, then it goes by a square root of 4. Sorry, square root of 2. So that's how the SNR decreases. And G is a factor called the geometry factor, which is related to the coil. And we want this G factor to be close to 1. Then the penalty you pay is less. So here in this plot, you see the comparison between a 8-channel coil and a 32-channel coil. So the G factor of a 32-channel coil is always less than a G factor of an 8-channel coil. So that's and that's how it helps in this parallel imaging. So in this example here, we see the accelerated image from 3 with an acceleration factor of 3 to 6. So even at such high acceleration factors, you don't lose. I mean, you can see the SNR is decreasing, but you don't lose much information. So that's the benefit of having these kind of high channel count coils. Okay, so that concludes my the first topic, which is a general introduction to transmit and receive coils. So in an MRI scanner, you need these two coils, a transmit and a receive. And the transmit coil, it flips the spin from the equilibrium position. It's always hidden behind the magnet board, and it produces a field which is very homogeneous. And the receive coil, it's to pick up the MR signal, and with the NMR phased array technique, we can simultaneously receive the signal from a larger field of view, and if you use an array of these surface coils, you can increase the signal to noise ratio. And I also spoke about activity tuning, which is to switch switch on and off these coils. And then increasing the number of receive channels will improve the accelerated imaging performance. Okay. So my next topic is the design of coils for ultra-high field. So what exactly is ultra-high field MRI? The name basically comes from the strength of the externally applied magnetic field, B0. So in this table, you can see the field strength of the different MRI scanners that are currently available. And the Lama equation, it provides the relation between frequency and the field strength for the atomic nuclei. And for the most commonly imaged nuclei, which is the hydrogen proton, this is the resonant frequency at each of these particular field strengths. Okay, so for 1 Tesla, the resonant frequency is about 42.58 megahertz, and at 7 Tesla, it's about 300 megahertz. So these are the field strengths that you see in a typical hospital. It's 1 Tesla, 1.5 Tesla, and 3 Tesla, and most of the high-end scanners will be 3 Tesla scanners. And anything above that is an ultra-high field. As Sydney mentioned, most of the ultra-high field scanners are at 7 Tesla, but there are now some scanners also at 5 Tesla. Okay, so these are the different field strengths that are currently being used in most of the research organizations. 7 Tesla is the mostly used one, and 11.7 is currently the world's strongest. This is in Paris. And there is another 14 Tesla scanner coming up in Netherlands, which will take another few years. Until then, the 11.7 is the current strongest, world's strongest scanner. So the main reason for going to ultra high field is to increase the signal to noise ratio. As you can see here, this is an example from this paper where they scanned the same volunteer in 3 different scanners. using 32 channel head coils from each of these scanners. You can see the SNR gain from the image itself, and this is the ratio between the 7 Tesla and 3 Tesla. The factor is more than 3, and between 7 and 9.74, it is close to a factor of 2. And this is the plot across the different anatomies in the brain. You can see this SNR gain is more than linear with respect to field strength, so across all the different tissue types. So that's really the benefit, or that's really the advantage of going to ultra high field. And this is a study, a recent study, where they used the same type of coil. This is called a tune-up coil that is supplied by Siemens. In the previous one, the coils, they used 32 channel head coils at different, which was the best at each of these scanners. So it was different coil types. This one is the same coil type. It's even then in this study, the conclusion was the same, that sorry. Sorry. Okay, so even in this study, the conclusion was same, that the gain in SNR is more than linear with respect to field strength. And this is a figure from a recent publication from the Neurospin group, where they scanned 3 volunteers at the same volunteer in 3 different scanners with comparable imaging parameters. And you can see the level of detail that you get at 11.7 Tesla compared to the clinical scanners, 3 Tesla and so on. But not everything is not straightforward. The ultra high field comes with a lot of challenges. It's basically a fundamental physics problem. It's related to the RF wavelength. As I've shown, when we increase the strength of the magnetic field, the resonant frequency increases. This means the wavelength reduces, and the wavelength in the tissue is reduced further by this relation, which is the square root of the dielectric constant of the tissue type. So this means at 7 Tesla, the wavelength is about 14 centimeters, which is shorter than the size of the head. So in this photograph here on the right, you can see this bit pictorially, that at 1 Tesla and 1.5 Tesla, the wavelength is larger than the size of the body. Okay. At 7 Tesla, the wavelength is smaller than the size of the head. So if you try to image the human body in a 7 Tesla scanner, you will have multiple of these wavelengths in the body across this imaging slice. That means you have the signal maximum and signal minimum, a multiple of them within the imaging slice. So you will end up with a really inhomogeneous image. So that's really the fundamental physics problem at higher field strength. So you can see this again here. When you go from 3 Tesla to 12 Tesla, for example, at 3 Tesla, you have a very homogeneous image, and this homogeneity decreases as we increase the field strength. You see this typical center brightening effect, and then there is this cancellation in the periphery. You can also see this in a different way here. This is the field produced by the coil. At 3 Tesla, it's quite homogeneous. And then you have this center brightening effect, and then you see the dark ring. At 11.7 Tesla, you see 2 of those dark rings. That's because the RF field behavior becomes highly complex at ultra high field. And there is constructive interference in the center, and then there is destructive interference in the periphery, which is about quarter wavelength away from the center. You see these dark rings. So for example, at 11.7 Tesla, because the wavelength is so short, you see 2 of these dark rings because of this quarter wavelength, which is quite short at that frequency. So these are initial results from a 4 Tesla scanner from Siemens. This was from the Siemens factory in the 1990s. They see this, in the brain image, they saw the center brightening. And in a body image, you can see it's really inhomogeneous, it's quite, it's a useless image that we just can't use anywhere. So they concluded, after seeing this, that they concluded that it is due to dielectric resonances, and they really stopped this project, because if it's due to dielectric resonance, then it becomes a safety issue, because it forms a resonance in the body and then it can heat up the tissue. And they stopped this project, and this scanner was then shipped to the University of Minnesota, where a lot of this scanner development, the ultra high field scanner development happened. So this is from a paper from the University of Minnesota, where they analyzed this dielectric resonance problem. So the two dots on the left, it shows the position of a surface coil. And this is a phantom, an image from a phantom, where they see that when the conductivity of the tissue is 0, they see so much more signal away from the coil. Okay, so that is because of dielectric resonance. It's a function of the solution that's inside this phantom, and also the frequency and so on. So you see so much more signal away from the coil, so which is due to dielectric resonance. But if you increase the conductivity of the tissue, you can see this resonance is dampening. And when you reach the conductivity level that's available in a human brain or a human tissue, this resonance is completely dampened, which means that the effect that they saw here is not because of dielectric resonance, it's because of something else. So, this is a field again. So I'm trying to explain what this is. So this is a field produced by a coil. This is an empty coil. That means there's nothing inside. At 64 megahertz and at 300 megahertz, it's quite homogeneous. But when you load this coil with a human brain or a human head, you see this, it's getting worse as we go to higher frequencies. And now you can see this, these bright dots. These are the current carrying elements of the coil. And the center of this coil is at equal distance from each of these current carrying elements. So what happens is that you have constricted interference because of all the phases they add the phases they're all in equal phase because the center is at equal distance. So it constructively interferes, and at about quarter wavelength away from the center, you will see destructive interference. So that is the reason for the center brightening and this darker periphery. So we have to find a solution to this, because in an MRI scanner you need a homogeneous magnetic field. Only then you get a good image. So the way to do it is, so here you can see this is the field produced by a volume coil. It's basically a complex summation of all the field produced by each of these current carrying elements. Okay, so if you now break this volume coil into a number of individual current carrying elements, so then you get the field produced by each of these current carrying elements separately. So instead of a single structure, you break the single structure into multiple of these individual structures. Okay, so then you get the field produced by each of these current elements separately. Okay, so then you can then apply, you can then influence the amplitude and phase of the current to each of these coil elements. And that way we can manipulate the field produced by the coil. Okay, so what we are doing here is we are going from a volume coil to an array of coil elements also on the transmit side. Okay, so when this concept was first introduced, this was many years ago in the 2000s, in the early 2000s, the MRI scanners didn't have multiple RF amplifiers, because for us to do this, we have to have multiple amplifiers. Then you can, on each of these current elements, you can apply different amplitude and phase, and then we can manipulate the field distribution. So those days, this was not available. So the way this was done was, this process is called static RF shimming. We have a single RF amplifier. The output from the amplifier is then fed to a power splitter, which gives outputs of equal amplitude. We can then change the phase of the current that is flowing through each of these outputs and that way we can manipulate the field. Okay, then during receive, so that's what happens during transmit. And when we receive, we acquire the signal just like in a conventional receive array. And then here, this is the image produced by the volume coil. So you have the center brightening and this periphery, darker periphery. And with this kind of a setup, we recover the signal in the periphery, and we get a much more flatter looking image. So the modern scanners, they look like this. You have multiple of these amplifiers. We have an array of amplifiers. Suppose we have an 8-channel system, then you have, or an 8-channel coil, a transmit array, then we will have 8 of these amplifiers operating in parallel. And then we can influence the amplitude and phase of the current to each of these coil elements. So we can also imagine this in a clinical scanner. You will have one amplifier like this, where in an ultra high field scanner you have 8 or 16 of this. So you can imagine how complex the ultra high field scanner is, because it's equivalent to 8 or 16 of the clinical scanners working in parallel. So it's really complex, and it's really expensive as well. Okay, so here, this is something I showed in the first topic. You have, in a clinical scanner, you have a transmit coil, and then you have separate receive coils. In an ultra-high field scanner, you cannot have a transmit coil for the reasons I explained just now. In the scanner, because you just need control over the amplitude and phase to each of these coil elements. So you will have a 7 Tesla coil will have a local transmit coil, as you can see here, and this would be an array coil. So here again, in these photographs, you see the difference. In a clinical scanner, you see a coil with only just a helmet like this. For example, it's a head coil. In a 7 Tesla scanner, you see the similar helmet, but there will be a transmit coil around that. Okay, so it's more like a helmet which is inside another tube. So you need local transmit coils, which are array coils as well. Okay, so that's the fundamental difference between a low frequency scanner and a high frequency scanner. Okay, so when this was first introduced, when this was first introduced, most of the transmit arrays were built using this microstrip transmission lines. A microstrip transmission line has a center conductor, which is a strip, and then it has a ground plane separated by a low loss dielectric material. Okay, and it's a distributed structure, so we can then calculate the dimensions of this structure, and then we can choose the resonant frequency of this structure. And instead, we can also keep the dimension of this structure constant, and we can then terminate the two ends of the structure with capacitors. That way, we have a fixed dimension, and then we can define the size of the coil more effectively. Then when you have more of these next to each other, they would couple, and then we can decouple them by using these capacitors, just by canceling the mutual inductance between them. And this is a 16-channel microstrip array that I built for the 9.4 Tesla scanner in Tübingen. So it's basically 16 of these microstrip elements, and each one of them is decoupled like this here. So this is the setup. We have a single amplifier. It goes to, because it's a 16-channel coil, you need a 16-channel power splitter, or 1/16 power splitter. And then the output from the splitter is fed through this TR switch circuit, which is here. And then we can use, we can connect different coaxial cables, and then we can change the length of the phase length, or the phase of the current to each of these coil elements. And this is the complete setup. So we have a 16-channel array coil, a TR switch module with 16 of them, and that's a power splitter, and there's a cable in between, which we can alter the length to change the phase. So here you see the image that is produced by this coil. In the upper slices of the brain, it's quite okay, but you see in slice 6 and 7 that it is quite inhomogeneous. And that is before shimming in the initial circularly polarized mode. Okay. Now we can then calculate and apply a phase, which will remove these dark spots, and then we get a much more homogeneous image. So that's the image before shimming, and that's the image after shimming. Okay. So here this is called susceptibility weighted imaging. This is a comparison between 3 Tesla and the 9.4 Tesla acquired with this coil. You can see so much more detail in the 9.4 Tesla image compared to what we see on the 3 Tesla image. Again, here there's so much more detail. Yeah, so that's really the benefit of going to ultra high field. Right. So when we build a coil for the head, you also want to cover the whole brain. So which is really a problem at ultra high field because it's much harder to produce a homogeneous field across a larger volume. So here you can see that this microstrip transmission array coil, it produces a good field on the top of the brain, but it falls off in the lower brain. And then if you try to image this lower brain, you don't get a good image. So here are some solutions to this problem. It's just not possible to just make the coil longer in this direction, but we'll have to arrange multiple of these coils in the longitudinal direction, and this way we can extend the field, the longitudinal coverage. And so in this, it's quite easy to understand from this example here. So this is a 1x2 coil where the coil is long along the Z direction, and as obviously it will then produce a field which is stronger in the center of this coil. So that's what you see in this plot here. But if you then break this up into 2x2 instead of 1x2, then you then alter the spatial distribution of this B1 field, as you see here. That means we are now extending the longitudinal coverage. Okay, so this is a 16-channel array which I developed for the 9.40 scanner in Tübingen. So here you can see it's arranged. The coil elements are arranged in 2 rows. There are 8 channels in each row. And all these coils are decoupled with this transformer decoupling, and there's kind of this rotation between the top row and the bottom row. That is to improve the decoupling between the diagonal elements, and you also see this integrated TR switches with preamplifiers. And this coil then operates in 2 modes. It's called because it has this TR switches, it can operate in the transceive mode, or you can then use it in the transmit only mode. Okay, so you see this is a large coil, but it has the transmit elements arranged in 2 rows. So you see the benefit of this kind of a design here. This is the circularly polarized mode. You see this typical center brightening, and you see this cancellation of this ring around this. And with this kind of a coil, because you have this, it's a dual row coil, you can shim in all 3 directions and so on. You can get rid of these dark spots, and you get a much more flatter looking image. As I said, that coil is a large coil. So, but if you want to maximize the signal to noise ratio, you want to come as close as possible to the anatomy that we want to image. So this is a receive coil that I built to work along with that coil. So this has 32 or 31 channels. It's arranged like this. It has all these preamplifiers which are integrated within this whole housing. The whole structure, and also they must be arranged in such a way that because this coil will sit inside the field produced by the transmit coil, you have to make this as transparent as possible, because you don't want to we don't want the receive coil to alter the spatial distribution of the transmit field. So that's all done here. And then you see the final setup. Here, this is the transmit array, and that's the receive array. When you put them together, that's how it looks. You cover everything with a nice housing and so on. It also has this periscope where for visual projection, so the people who are getting scanned, they can see through them, see through these periscopes. Okay, so now you see the comparison of these two coils, and the first one is the microstrip array, and then the new coil, because this now has this 16 transmit and 31 receive. You get so much more SNR with this new coil. In both these regions here in mask 1 and 2, you see the SNR gain is more than a factor of 2. So these are some in view images that were acquired with this coil. With this has a resolution of about 260 micron. This was acquired in less than 5 minutes. And here again, these are images from the same coil with the resolution of about 300 to 330 micron. This is 250 micron. The important thing is to note that even at 9.4 Tesla, with these kind of coils, you can get whole brain coverage and this kind of nice resolution comes automatically because of the high field. But the important thing is that even at 9.4 Tesla, with these kind of coil designs, you can get whole brain coverage. Yeah, so we can categorize these kind of coils, ultra high field coils, in two groups. And the first one is transceiver coils, where we use the same coil to transmit and receive. And then it's a transmit only, receive only coils, which is the one I showed just now, where we have a separate transmit and a separate receive coil. So with this kind of transceiver coils, you can bring the coil close to the head, so then you produce a much stronger V1 field. Whereas in this kind of coil, you want to have space for the receive coil, so the transmit coil will be large. So that way, you will see that the field produced by this by this kind of design approach it's weaker in the periphery. You have this constructive interference in the center, but it is weaker in the periphery. That's because you need space to place a receiver array. But if you look at the signal to noise ratio, that's what we really want. And if you look at the signal to noise ratio, you see they're so much better than these transceiver arrays. So the examples I showed until now, these are 9.4T coils, and these are a couple of 7 Tesla coils that I built, and this is in collaboration with the University of California, Berkeley. And this was recently published in Nature. So the first one on the top, that's a 16-channel transmit. It's a dual row design in combination with the 96-channel array. And finally, it's all enclosed in a nice housing, so you don't see any of this outside. And the second row here, that's the 8-channel transmit, 64-channel receive head coil. That's again, these two coils are now being used at the next gen 7 Tesla scanner in Berkeley. So this is the world's first 96-channel 7 Tesla head coil. And you can see, or you can appreciate how complex it is. So there's some photographs of this coil. And it's also because, as I said, it's within the field produced by the transmit coil. You have to make sure that it doesn't interact with the transmit coil and so on. So all of the way this is constructed and arranged and how the electronics is placed and so on is very critical in these kind of coils. So why do we want to go to this kind of complex designs? Here you have the answer. This is the industry standard NOVA 32-channel head coil. And with the 96-channel coil, you produce so much more SNR in the cortical layers of the brain. And in the center also, we get similar SNR. And then these are SNR maps in the sagittal and the coronal plane, where you see so much more signal in the cortex. That's really what the neuroscientists are looking for. They are looking for higher resolution in the cortical layers of the brain. So again, this is a comparison between a 32-channel and a 64-channel coil. And As I said already, when we increase the number of channels, then you gain in parallel imaging performance, and the G factor for a higher channel coil is always lower. So you pay lesser penalty. And this is what you see here. There are two regions of interest, one in the center of the brain, which is marked in red, and the periphery is marked in blue. You see it without acceleration, they are quite comparable, the two coils, 32 and 64, but as you increase the acceleration factor, you get so much higher SNR with the 64 channel coil. So here you can see this gain in a real application. This is 32 versus 64. This is 1.5. That's that's not a very good resolution, and also acceleration factor of 3. You don't see much of a difference here. But if you then increase the resolution to 0.8 millimeter isotropic, and then you increase the acceleration factor to 4, 5, and so on, you really see the difference here. And for example, at 5, you just can't use the 32 channel coil. This is again an image from the Berkeley scanner where we can see the whole brain coverage with nice homogeneity across the slice and very high resolution and so on. So to summarize my second topic, so MRI at ultra high field is challenging due to shorter wavelength in tissue, and you really need parallel transmit arrays to mitigate this transmit field inhomogeneity that is caused by the shorter wavelength in tissue. And you need this dual row transmit array coils to extend the longitudinal coverage. And if you combine transmit arrays with these high density receiver arrays, you can improve the SNR. And as always, when you increase the channel count of the receiver arrays, then it improves the parallel imaging performance. Okay. Okay, so I go to my last topic, which is a case study on commercialization of academic research. So this is part of a program called the Living Laboratory Program, which is led by the University of Glasgow. The aim of this program is to translate science and innovation into products for clinical use. The coil development program is one of the sub-projects within this Living Laboratory Program. And we have identified 5 different 7 Tesla coils for different body parts. And they are in different stages of development at this point in time. So I'm going to talk about the head coil is the most advanced. So I'm going to talk about the journey from the university lab to a commercial product. So this is the Queen Elizabeth University Hospital in Glasgow. This is the largest acute care hospital in Western Europe, and the ICE building is the University of Glasgow building, which is based within the hospital campus. So almost on all projects in ICE, you will see the university researchers and the clinicians from the NHS working together. And the top floor in this building is reserved for companies. The vision or the idea from the college management was that this would then facilitate collaboration between university researchers, NHS clinicians, and industry partners. So this way, we can then accelerate the innovation from the university to a commercial product. The company MR Coiltech is also based in this building. As I said, it's in the top floor. This is the 7 Tesla scanner which is located in the ground floor of this building. And this is the only 7 Tesla scanner in Scotland, and there are 7 of them in the UK. And the difference is this is fully integrated in a hospital environment, whereas most of the other 7 Tesla scanners are in universities. And next door to this scanner, we have a coil lab for the university, and then there's a company coil lab in the top floor. So there are 2 different coil labs in this building. So a maturity level of a technology, you can define them with respect to this technology readiness levels. You go from basic or applied research, which usually happens in a university. Then we undertake the translational development, and then you have to clinically evaluate them, and you get regulatory approval, and then you have to disseminate them. So basically, you need funding for all of these different activities to go from basic research to clinical evaluation to safety and regulatory approval. You also will notice that you really need a wide range of expertise going from academic research to industrial development to clinical evaluation to regulatory, marketing, sales, and service. What you also so you really so it's really hard to find all of this expertise in one place. Typically, you see them in different companies, sorry, in large companies. Whereas in small organizations, you don't find this range of expertise. So this shows it's really important for the different organizations to collaborate. This plot also shows the funding landscape that's available in the UK for the different technology readiness levels. So depending on the readiness level of the technology, you apply for different grants. Okay. So before that, you have to have an understanding of the market. This is the 7 Tesla market. There are about 120 to 157 Tesla scanners operating worldwide, mostly in the universities. Slowly, they are getting into hospital environment. And in about 3 years' time, I think it's expected to cross 200. And Siemens is the most dominant MRI manufacturer. They control 70 to 80% of the market share. And this shows the different applications in 7 Tesla MRI. You can see most of the scans are 7 Tesla scans. Sorry, most of the scans are head scans. So the neurological scans is imaging the brain. So this means a head coil for 7 Tesla is really important. Okay. The price of a head coil is about $300,000 to $400,000, and so this means that it is, even though the volume is very less, it's a low volume but a very high value market, and we are looking about $60 to $70 million in terms of the market. So this is the Siemens 7 Tesla MRI scanner. This scanner operates in two modes. They call the STX mode and the PTX mode. And in terms of configuration, it has 8 transmit channels and 64 receive channels. And this is the current industry standard 7 Tesla head coil. They have 2 coils, one for STX and one for PTX. It's from a company called Nova in the US. And you need separate coil for these scanner modes. And it's important to note that these coils are FDA and CE approved. So that means they are approved by the regulatory authorities. But although the scanner has 64 receive channels, this coil has 32 channels. So this means we are not really utilizing the scanner to its full capability. Okay, so when I joined the University of Glasgow a few years ago, I was given some seed funding to set up the lab, and I also got some money for a coil. So I chose to design a head coil, and this locally we call it the Glasgow head coil. In terms of configuration, it has 8 transmit channels and 32 receive channels, and I worked with the clinical colleagues to derive the requirements for this coil. Basically, this coil operates in. So we want to use the same coil to operate in STX and PTX mode, so that you don't need you don't need 2 separate coils. And then we wanted the coil to be less claustrophobic, and the clinicians also wanted a mirror system so that the patients can see the operator when they are getting scanned. And we also wanted the coil to be friendly in terms of operator comfort and patient comfort and to improve the clinical workflow and so on. Long story short, and this is the 2D layout of the 8-channel transmitter array which I developed. We call it the nested 8-channel transmitter array. So it has 8 conventional loops which are shown in red and black, and all the adjacent channels are critically overlapped to cancel the coupling. And there's a nested arrangement of loops to decouple the next neighboring channels using the transformer inductors. Um, okay, right, okay. So the decoupling in the center is different because we wanted to have space for this large cutouts. If you have this overlap here also in the center between 1 and 8, then the size of this cutout will be smaller. Okay, it's also not as simple as putting a hole in the plastic because the coil is an antenna. You really it also has an RF shield, so we are making cutout in the RF shield. So we had to balance the magnetic field distribution of the coil. This is the photograph of the coil that was developed. So there, you can see the geometric overlap, and then these inductors and this large cutout. Okay. So this is a receive coil which goes inside the transmit coil. It's also a redesign of the 9.40 coil that I showed earlier. And this is the final setup. You can see the front view and the back view, and also the large cutouts. And on the right, this is a power splitter. This is for this dual mode function. This would then allow us to use the same coil in both STX and PTX modes. So if we use the coil in the single transmit mode, then we drive the coil through this power splitter. The single output from the scanner will go into this BNC connector, and this power splitter, it creates 8 outputs, which is then used to drive the transmit array. So this design was granted a US patent, and this means that the design of the coil is protected. And this is then quite important when we go for funding the grant applications in the later stage, because they always want to see if the design is protected. Okay. And the safety of the coil is very important. That's a huge topic in itself. I've completely ignored that because of time. And in the Siemens system, the management of the power to the coil, it's managed by a method called virtual observation points. And in Glasgow, we were also the first group outside of Siemens to implement this method. So what we do is we generate a very accurate model of the electromagnetic model of the coil in an EM simulation tool. And then we also simulate very different body models. For example, you have male and female of different age groups and of different sizes and so on. These are then converted to something called these SAR values are then converted to something called a Q matrix. And then all of these different simulations are then concatenated into a single Q matrix. This one Q matrix would be a huge file with millions of voxels, which would then, it will be too much for the scanner to handle. So there is a compression method called the VOP method, which is then used to compress these millions of these voxels into a few hundreds of data points. And this file is then loaded in the scanner, and the scanner will use this information to control the power that's going to the coil. Okay. So once we have all of this set up, then we can then we can scan this coil in the scanner. And here you see the comparison. This is field produced by the coil in a phantom. We compare this commercial coil with this Glasgow head coil, and we see that it's quite comparable. We are, in this case, on the transmit side, we are about 5% or so less. That's because we have these large cutouts, which because of that we reduced some field, but that is something we wanted to incorporate this large cutout. So that's something was a compromise that we were willing to take. So here you see the comparison between the commercial coil and our coil. You see much more of the cerebellum here. So we have a longer longitudinal coverage. And also in the lower slice, we see so much more information, or we see more information in the lower brain compared to the commercial coil. Right. So that means that we have now demonstrated the proof of concept in a laboratory environment. We have demonstrated the safety and efficacy of this coil in a laboratory environment, in a real world environment. So we are then moving forward in this TRL level, and then we have to look at if you want to translate this design to the next phase, next stage of clinical evaluation and so on, then we have to look at this funding landscape and see what is appropriate for us. And we chose to go for this Innovative UK application, or this Innovative UK grant. So basically, they support early stage commercialization of innovative projects, and the project must be led by the industry. And this must be collaborative projects between academia, industry, and NHS. And they also want to emphasize or give importance to the companies. So that means 50% of the project cost must be within the industry. So these are the conditions for the grant. So this is what we pitched to the grant giving body. These are the 4 advantages. We have the Glasgow head coil compared to the commercial coil has whole brain coverage. We have dual mode functionality, which means that you need only one coil for the 2 scanner modes. That means the customer will have to buy only one coil instead of 2 coils, so which gives them a competitive advantage in terms of that we are not doubling the cost of the coil. And the other advantage, as I mentioned earlier, is this claustrophobia. So when you have a closed design, it's quite uncomfortable for the subject. As I explained already, we had to modify the antenna design using electromagnetic simulations to incorporate these 2 large cutouts. So we can then attach a lookout mirror for the patient to see the operator when they are getting scanned. And our coil is also more compact, so it's about 3, and it is shorter, about 220 to 30 centimeters. It also weighs less, about 3.5 to 5 kilos. So that way, it's easier for the operator to handle the coil in a clinical environment, and it also optimizes the workflow. This grant application was, there were 4 partners: MR Coil Tech. White Blue is a Glasgow-based company. They are experts in product design, and the imaging part of it was led by David Potter from Glasgow University. And the clinical, the device evaluation was led by NHS, by Natasha from the NHS. So there were 373 applications in total, and only 8 of them were successful, and ours was one of that. And basically, the grant funded development of an industrial version of the coil, implementation of the ISO 13485 quality management system, developing MR imaging methods, and then also device evaluation study, and also to perform comprehensive electromagnetic simulations. So this is the model or the coil that the White Blue engineer came up with. So basically, you see it looks so clean from the front. The way it's arranged, the way the whole thing is assembled, it's all pushed to the back. So only on the service end, you see a lot of screws. But from the patient end, it looks really clean. And you have this lookout mirror for the patient to see the operator during the scan. And we also implemented this sliding mechanism, which means that the receiver is split in 2 halves, and there is this sliding. The patient will lie on the bottom, the posterior half, then we close the anterior, then we close this one. So that's the final scan position. At some point during the during this project, we decided to go to a 64 channel design because as I said earlier, the scanner, the 7 Tesla Siemens scanner has 64 channels, whereas the current industry standard has only 32 channels. Okay, so we decided to go for a 64 channel coil. So here is this is data from the University of Minnesota. Our coil is currently called the NeuroCam 70 coil, and these are the two NOVA coils. We see the comparison between the NOVA and our coil. Because it has 64 channels, there's so much more signal in the periphery, and we perform quite comparably in the center. So here you see the ratio between the NeuroCam and our NeuroCam and the NOVA coil. So we have about 40 to 50% more SNR in the periphery, and we get similar performance in the center. So this is the G factor comparison between the Glasgow 64 channel coil and the Nova 32 channel, showing that we always perform better when you have more number of channels. So this means it gives us more acceleration factor. Then is the device evaluation study, which was led by Dr. Natasha Fullerton from the NHS. So we scanned 15 volunteers, and they were scanned in 45 different sessions because we had we had our coil in STX and PTX mode, and then the NOAA coil as well. And as part of it, the operator and the patient, they all had questionnaires to assess the quality workflow and everything. And then it also had a questionnaire for the image quality, which was then assessed by 4 different radiologists. So these are some images from this evaluation study. And the coil performed as expected, and we have very good image quality in all of these images. And this is from this evaluation study where we show that our coil performs equally or better than the NOVA head coil in terms of image quality and diagnostic quality and so on. And again, this is from the operator and patient assessment, how friendly the coil interface is, how good the coil is handling and clinical workflow and so on, showing that we perform equally well when compared to the current industry standard coil. Okay, so this is what I started with. This is the university prototype, and then on the right you see the industrial version of the Glasgow head coil. Okay, so there you see the transformation, basically going from a university prototype to an industrial version of the coil, which was basically funded by this Innovate UK grant. So we now have this was developed a couple of years ago. We now have this coil in a few of these universities. Obviously, there's one in the University of Glasgow. We have one in Maastricht in Netherlands. There's one in the University of Magdeburg in Germany. There are a couple of them at the University of California, Berkeley. There's one at the MPI in Leipzig, NIH, Vienna, and the University of Minnesota, and then also Liège in Belgium. Right, so I want to introduce another small topic called magnetic field monitoring. What exactly is magnetic field monitoring? It means that when there are magnetic field fluctuations during an MR image acquisition, which leads to reduced image quality and artifacts. Okay, so there are a wide variety of sources which can cause these fluctuations. For example, if we are scanning for a long time, let's say we are scanning for 30 to 40 minutes and so on, all the electronics in the scanner and also the coils and everything heats up. This can cause drifts in the magnetic field. There are also variations because of physiology. For example, we are breathing in the scanner, so there is movement, and so this causes magnetic field fluctuations. And there are also electronics noise. For example, there are eddy currents induced in the gradients and the shim coils, which can cause magnetic field fluctuations. So at ultra high field, we are really looking into very high resolution images. So all of these little things can cause a problem. I mean, we reduce the image quality. That's what I mean. So with concurrent field monitoring using these field probes, we can monitor these kind of field dynamics, and then with this information, we can then correct this magnetic field fluctuations. So these field probes are developed by a company called Scope. They are based in Switzerland. It's now owned by Canon, and they are really the specialists in this magnetic field monitoring probes. Okay, so this is the current setup. It is very experimental. You can see they need about 16 probes. They must be arranged in a constellation so that we pick up all these fluctuations from the whole brain volume. And you can also see from each of these probes, there is a cable and it goes to their electronics and so on. So the whole setup is quite cumbersome and it is experimental and just not practical in a clinical environment. So the idea of this project is to integrate these field probes inside the coil, inside the Glasgow head coil, and so that we get a much more elegant setup. So this is our finalized product. This is the Glasgow head coil with this with the field probes completely integrated inside the coil. So these are these are miniaturized versions of the probes that I showed earlier. There are 16 of them arranged inside the coil. We also had to move the electronics and the PCBs and the circuit boards and the circuit elements and so on inside the coil to accommodate these probes, because these probes are very, very sensitive. So the environment and surrounding the probes are very crucial. But we integrated 16 of them inside the coil housing. And finally, from externally, it just looks like the normal coil. But you can see here the probes are fully integrated inside. And when we put in so much more electronics inside the coil, we also have to make sure that we are not creating any safety issue. The probes are not heating up. The probes are not altering the spatial distribution of the B1 field and so on. So here you see this is simulation on the left. This is without probes and with probes, and you see there's hardly any difference between the two scenarios because we were very careful in placing selecting the positions or the locations of the probes and so on. And on the right, this is the experimental measurement where we show the field map without the probes and with the probes, and that's the difference here. When we see some difference only when we multiply by a factor of 10. So basically, the probes are very well integrated inside the coil. And you can also see here, these are SNR maps showing that there's hardly any difference when the probes are integrated. So this means that we don't have to include, the probes are transparent and we don't have to include these probes in our simulations and so on. But we have two of these coils now, one at the Max Planck Institute in Leipzig and there's one at the University of Minnesota. This is how the final product looked like. So on the right here, you see it's all completely integrated. You don't have 16 of these cables coming out in the visual field and so on. And then the front end electronics for the probes are attached to this housing at the back, as you see here. You will also notice in this particular photograph, the cutout of this external mirror is missing. That's because this is a 16-channel array. In a 16-channel transmitter array, it's really complicated to incorporate these cutouts. Only on the 8 channels we have this. Anyway, so this is now a product which is now marketed by Scope and Canon. You can see more of this product information in their website. There are 3 versions of this. One is the standard version, where it's just the coil. It's just the basic coil, which I showed earlier. And then there's a middle version, which is an advanced version. And then there is a excellence version, which is fully integrated version. Right. So what next? We want to get regulatory approval for this coil sometime this year, early next year. That's our goal for the next 12 to 15 months. And we want to get this listed as part of the Siemens accessories catalog, because they are for that to happen, we have to have the regulatory approval. That's what we are working on. And as I showed, we started from TRL level 1 and we are somewhere near 7 or 8. So with the CE approval, we will go to TRL 9. So that's where we have progressed from the university prototype. Right. So that's my last slide. So I want to acknowledge those who contributed to this project. It's a huge program with high importance at the University of Glasgow. So Anna, Carol, and Ruth, they are from the college management team. The Living Laboratory project is their idea. It's their brainchild, and a lot of funding for this development came from the Living Laboratory project. And then we have my colleagues at the University of Glasgow and my colleagues at NHS. And as I said, I work very closely with the University of California, Berkeley. And the David Feinberg is the PI, the principal investigator there. And I work closely with Siemens as well, and of course Scope, and then McCoy Tech. Yeah, that's it. And thank you so much for your attention.
Participants, any questions? As we come to the end of this enlightening session, it's my privilege to extend a heartfelt vote of thanks on behalf of Marthanam College of Engineering and Technology. I would like to convey my sincere gratitude to our esteemed resource person, Dr. Shajan Gunamani, for taking the time to share his valuable insights on how to design a radio frequency coils for UHF MRA. Sir, your expertise and the thought-provoking discussion have provided the wealth of knowledge and inspiration. We truly appreciate your effort and generosity in imparting your wisdom. Thank you, sir, for generously sharing your time and expertise with us today. Thank you, sir. Next, I thank to our organizers, faculty, and supporting staff for making this session a grand success. I also extend my gratitude to our enthusiastic participants whose presence and engagement added value to today's event. Thank you all and have a wonderful day.
Thank you.
Thank you, sir.